Hello everyone, and welcome to this video, section 3.4, called Partial Fractions. In this video, I'm going to be taking you through a preview version of a Newton-Alta assignment for this partial fractions section. Please understand that the questions I see in this video may not be exactly the same questions that you see if you were to work on the assignment yourself. But I'm hoping that the objectives are the same and the problems are similar enough that watching me do them here will help you when you work them on your own. All right, so here you have a page with the preview of the assignment, right? You won't see the word preview, but you'll have the title of the assignment. Upper right-hand corner, you got your mastery bar telling you how far along you've gotten. Your activity log, which shows you how far you've gotten in each objective. So it looks like there are the 4 objectives here. Then you have an objective, right, and a question related to that objective. And beneath the question, you should have a feedback button. So if you're noticing a typographical error or something wrong with the answer explanations when you get them, anything wrong at all, you can send feedback directly to Newton, and hopefully they'll get back to you and help you out. You will not have this instructor cheat button, right? This is for instructors only. You will have a more instruction button. So if you're ever struggling with a particular objective, particular question, try clicking on the more instruction button, and it should take you to a page where you get either further reading to do or videos to watch or both. And then you'll be given questions related to that instruction, related to that objective, and you can work your way through the assignment that way. And something I've not done in previous videos involving Newton-Alta, we now have the option to switch objectives. I've toggled that on, finally, to switch objectives in the middle of the assignment. So another thing you could probably do if you are struggling with an objective, get out of there for a minute, switch to a different objective, see how that works out. And then maybe practice problems from your textbook or some other source until you get more comfortable with the topic. And then come back and work on problems from that objective again. So actually, I will be doing this. I will be doing this switch, so that way I can get a bunch of problems in a row from the same objective. Right, and I'm just going to finish one objective at a time, right? So you got your 4 objectives here, and I will work my way. I'll start with this integrate a rational function using long division of polynomials, and then I'll work my way through these 3 objectives where we're integrating, using partial fractions. Okay, I'll show you how to do that switch later. All right, so my first objective, integrate a rational function using long division of polynomials. So we're integrating in this section rational functions, right? Ratios of polynomials, so polynomial over polynomial. In this objective, we'll see rational functions that are improper fractions. So you might recall from a previous algebra class or pre-calculus that an improper fraction, an improper rational function, the degree of the numerator polynomial is either the degree of the denominator polynomial or greater. So in this example here, we have a degree 3, a cubic polynomial in the numerator, and a degree 1, right, some smaller degree polynomial in the denominator. All right, so what we're going to be doing every time we see an improper rational function, First, we're going to perform long division. Divide the numerator by the denominator, and then rewrite it as quotient plus some proper fraction, quotient plus remainder over divisor. So hopefully this will be a nice refresher too as to, how to do polynomial long division. Okay, so let's write this integral out on the paper. So we have the indefinite integral of, again, an improper rational function, 5x cubed minus 2x squared minus x plus 1 over, and then the denominator polynomial, x plus 1. All right, so like I was saying, this fraction I'm seeing here is what, they'd consider this improper by definition. And if that's the way your rational integral is starting out, perform long division. All right, I'll just write divide here. All right, so I'm going to ignore the integral and the differential for right now. We'll come back to that. I'm going to divide 5x cubed minus 2x squared minus x plus 1 by x plus 1. So I write my long division symbol. It almost looks like a square root, but it's not. The numerator goes underneath it. I'm putting them in descending order, 5x cubed, then the 2x minus 2x squared term, and then the minus x, then the plus 1. And the divisor is your denominator, right? That goes on the outside over here on the left side of the symbol, x plus 1. In descending order, again, I'll do write them both in descending order. All right, so again, to hopefully refresh your memory, I'm not going to write these steps out. I will just say them out loud. First, you divide the lead terms. 5x cubed divided by x. So that would be 5x squared. I'm going to put that up here above the bar here. This is where your quotient is going. And then whatever term I just wrote, I multiply by the divisor. I multiply 5x squared by x plus 1 and write that result underneath the original dividend, the original polynomial I was dividing into. So we multiply 5x squared by x plus 1. Well, 5x squared times x is 5x cubed. 5x squared times 1, positive 5x squared. Right. So you divide the lead terms, multiply by the divisor, and now we subtract. So I take the polynomial I started with and then subtract. Now be careful with this. You got to subtract the entire thing I just wrote, the entire polynomial I just wrote, not just the first term. So I like doing this with the parentheses. Subtract this polynomial from the one above it. Now 5x cubed minus 5x cubed would be gone. That's 0. Negative 2x squared minus 5x squared. Don't forget you're distributing the negative here. You're subtracting everything. Negative 2x squared minus 5x squared would be negative 7x squared. And then we have negative x minus, there's no x here, so just negative x still. And then 1 minus, and there's no constants here, so plus 1 still, positive 1 still. All right. And then you keep doing this. Divide by the lead term, multiply by the divisor, and subtract. Divide, multiply, subtract, divide, multiply, subtract. You keep doing this until the polynomial you get after subtraction has a degree that's smaller than the degree of the divisor, right? So I can't divide the lead terms anymore. So this after subtraction, I have a degree 2 polynomial, this negative 7x squared minus x plus 1. That's still the degree of the divisor or higher, so I can keep going. So again, same steps. I divide the lead terms right now with this one. Negative 7x squared divided by x is negative 7x. Right. Then I take the term I just wrote, negative 7x, multiply it by the divisor, negative 7x times x, and write it underneath this previous polynomial. That's negative 7x squared, and then negative 7x times 1, negative 7x. So I've done divide, I've done multiply, now subtract. This polynomial I just wrote, all right, subtract all of that, right, so we'll be distributing the negative here. Subtract all of that from the polynomial above. Now anything minus itself is 0. Negative x minus negative 7x would be plus 7x, so negative x plus 7x, positive 6x. And then 1 minus, and there's no constants here, so still 1. Now after subtraction, the degree of my polynomial now is 1, but that's still the degree of the divisor or higher. So I can go one more time here. All right, divide the lead terms. So 6x divided by 1x. That'd be positive 6. All right, so I write positive 6 in the quotient area. Then we multiply by 6. 6 times x plus 1. 6 times x, 6x. I write it underneath the previous polynomial line. 6 times 1, positive 6. And we subtract all of that. All right, subtract the entirety of that from the line above it. Now 6x minus 6x is 0. 1 minus 6, negative 5. Right. So there, and now the degree of negative 5, right? Negative 5 is a constant that has degree 0, and my divisor had degree 1. So I'm done now, okay? After subtraction, if the degree is smaller than the degree of the divisor, you are finished. So we have here above the bar, it's 5x squared minus 7x plus 6, right? This is called the quotient. It's basically like how many times x plus 1 goes into 5x cubed minus 2x squared minus x plus 1. And then down here, after that final subtraction, this negative 5, that would be considered the remainder. Right. So I can write this fraction now as quotient plus remainder over divisor. The quotient plus some proper fraction. So let me cover this up here. So, this integral that we had, the integral of 5x cubed minus 2x squared minus x plus 1 divided by x plus 1. I'm going to rewrite this fraction now as the quotient, which was 5x squared minus 7x plus 6, right, quotient plus some improper fraction, which is going to be the remainder, negative 5, over the over the divisor, right? Because everything's being divided here by x plus 1. Right? So if I write plus, the remainder, negative 5, over the denominator, right? The divisor, x plus 1. This expression right here is equivalent to this fraction. It's the result of dividing this numerator by this denominator. And then, of course, you got your dx. And now writing it this way, where I have quotient plus, proper fraction. Right, and we'll deal with proper fractions in the last 3 objectives of this assignment here. But this would be considered, right, a proper fraction. the degree of the numerator is smaller than the degree of the denominator. And, again, we'll hold most of the rest of the video. 3/4 of the objectives are dealing with proper fractions. But now that I have it split up like this, quotient plus proper fraction, I can integrate much more easily, right? Especially because, look at the quotient. The quotient is a polynomial, and I can easily integrate polynomials term by term using the reversal of the power rule. 5x squared, right? The integral, the antiderivative would be 5/3 x cubed minus, and then 7x, the antiderivative would be 7/2 x squared plus 6, right? Plus 6x when I do the antiderivative there. So there's my antiderivative of the quotient. And then we have plus, -5, so -5. And then the integral of 1 over some linear is the natural log of that linear, and then divided by the coefficient of the x, right? Because if it was 2x here or 3x, I'd have to divide by 2 or divide by 3 when integrating to counteract the chain rule. But this is just 1x plus 1. So this ends up being, -5 times the natural log of the absolute value of x plus 1, right? Very simple antiderivative there. 1 over some, linear polynomial. And there we have it. This is our primitive antiderivative or basic antiderivative of this rational function. And then, of course, with any improper fraction or improper integral, not improper, sorry, indefinite integral, you can always throw on any constant here and it would still be an antiderivative. And there we have it. All right, so here's what I'm going to enter into my assignment. Now, if you'd like to check this, take the derivative of this expression, you'd get this, which if I were to put these together and get a common denominator here, you'd get this, all right? And I'll leave that to you to double check. So I'm not going to be really checking things in this video, I'm sorry to say, because I feel like it's going to be a long one. All right, so back to the assignment. All right, I will enter what we just had there in the box. So I have 5/3 x cubed minus 7/2 x squared plus 6x and minus 5 times the natural log of the absolute value, that symbol's right there, the absolute value of x plus 1, and then get out of that absolute value, and then plus some constant, right, plus c at the end. Submit it. Submit it. And I'm correct. Hooray. Now, after every question, you are given an answer explanation, and this is whether you are correct or incorrect. I'd recommend reading through them, or at least skimming through them either way. If you're correct, but, they do it some other way that you like better, which it doesn't look like they did it any differently than I did. But if they do it some other way that you like better, you might want to try that for future problems in this objective. Now, of course, if you got it wrong, definitely read through the answer explanation and see if you can figure out, where you went wrong, why you were wrong. Or maybe you could catch a mistake and send them some feedback. All right, so moving on, we'll get another question in this objective. We're going to be able to finish this one up first before the others. So again, I'm giving an indefinite integral of some improper rational function, right? The degree of the numerator is the same as the degree of the denominator, right? It's not less. Proper fractions, the degree of the numerator is less than the degree of the denominator. So I'm going to do the same thing I did with the last one. I see an improper rational. We're going to do division first. So here's my integral. So we have the integral of, and then the rational function here is 5x squared plus 12x plus 17 over, x squared plus 2x plus 3. All right. And then, first times your differential. But once again, I'm seeing this is an improper fraction. So I'm going to rewrite this using division. Let's divide the numerator by the denominator. So again, law and division symbol. Got numerator inside in descending order. And denominator, the divisor, outside. Also in descending order. The steps here, same, divide, multiply, subtract. Divide, multiply, subtract. Divide the lead terms. 5x squared divided by x squared. Just 5. Then multiply by the divisor. 5 times x squared is 5x squared. 5 times 2x, positive 10x. 5 times 3, 15. And then you subtract all of that from the line above it. 5x squared minus 5x squared is nothing. 12x minus 10x, that'd be 2x. 17 minus 15, positive 2. And that's it. The degree of this is 1. The degree of my divisor is bigger. So I'm done. I'm done with the division. My quotient is 5, and the remainder is this 2x plus 2. So now I'm going to write this integral as the integral of, something equivalent to my original fraction, which is 5 plus, that's the quotient plus remainder over divisor, 2x plus 2 over x squared plus 2x plus 3. All right. So I can break this up. Let's go term by term here. Now the first, the integral of the quotient should be easy again, right? The quotient's just a polynomial, just 5. So that's 5x. Easy, right? 5x. Now look at this next integral. It's a proper fraction, right? The degree of the numerator is now smaller than the degree of the denominator, but there's something really nice about this fraction here. This doesn't always happen. Okay, we'll see problems later, I'm sure, where this doesn't always happen, but if you look at this, the denominator is x squared plus 2x plus 3. The derivative of the denominator would be 2x plus 2. The derivative of the denominator is the numerator. So look at this u sub I'm going to make here. This is going to be real nice. If I just replace the denominator then with u, say u is x squared plus 2x plus 3, then du, right, would be 2x plus 2 times dx, and that's exactly what we have in the numerator here. So we have du in the numerator, and then u in the denominator. So I'll write that out. All right, so we got 5x initially, right? That was the integral of just a quotient. And then I changed this to integral in terms of u of just du over u, right? The derivative of the denominator was the numerator. You got du over u. And that's just a simple natural log of the absolute value of u. So we have 5x plus the natural log of the absolute value of u, but then remember what u was and put it back, right? We got to go back. The original integral was in terms of x. I would like my answer to then also be in terms of x. So my final result, 5x plus the natural log of the absolute value of x squared plus 2x plus 3. And then, of course, for all the indefinite integrals, right, plus any constant. Right, and that's what I'm going to be taking. So back in the assignment, 5x plus the natural log of the absolute value x squared x plus 2x plus 3, which is actually always going to be positive, so I really don't need the absolute values around that. But anyway, right, for any real values of x, but I'll just keep the absolute values because they are asking for them in the instructions here, right? And then plus any constant, plus c. And I hit submit. I was like, anytime now. There we go. Got it correct. Hooray. Answer explanations. All right. Moving on. The third question from this same objective. So yet again, I have an improper fraction. Right? So once again, see an improper rational function. Let's start with long division, right? Rewrite it as a quotient. The quotient will just be a polynomial plus the remainder over the divisor, the remainder over the denominator, which will be a proper fraction, and go from there. So our integral is, the integral of x squared plus 5x plus 7 over x squared plus 3x plus 4. Okay. So again, I see that this fraction is improper. Right? The degree of the numerator is not less than the degree of the denominator. So first step here is going to be divide. Rewrite this fraction as a quotient plus a proper fraction. So I set up my long division again, numerator inside in descending order, denominator outside in descending order. All right, divide the lead terms, x squared divided by x squared, that's just 1. Multiply 1 by the divisor, you get, 1 times x squared is x squared, and then 3x, and then 4. And then we subtract all of this from the line above it, right? Subtract every single term, not just the first term. X squared minus x squared is nothing. 5x minus 3x, that's 2x. 7 minus 4, positive 3. And I'm done. This is the remainder, right? The degree of this is smaller than the degree of the divisor. So now my integral looks like this. I'm rewriting this fraction as 1 plus this remainder, 2x plus 3, over the divisor over the original denominator, x squared plus 3x plus 4. All right. Now, the integral of 1 is easy. That's just x plus, and then once again, okay, so I'm not going to do a u sub here. I'm just going to say if I was looking at this integral here, this fraction, this proper fraction, once again, the derivative of the denominator is the numerator. The derivative of x squared plus 3x plus 4 would be 2x plus 3. So this is just like the previous example. And if you have an expression where the derivative of the denominator is the numerator, then it's just the natural log of the denominator. So that integral is the natural log of the absolute value of x squared plus 3x plus 4. Okay, and then of course plus any constant, and we have it. Right. Now, if you wanted to do that integral separately and do the u sub, let u be the denominator, again, you would just end up with du over u, the natural log of the absolute value of u, and then put the x squared plus 3x plus 4 back in. So I'm writing this out in my assignment. So x plus natural log. And again, they want us to have arguments of logarithms to have absolute value signs when submitting. So natural log of the absolute value of x squared plus 3x plus 4. And after that, right, plus any constant z. Takes a bit for them to check these, doesn't it? And there we go. Great. All right, so next question, also from this same objective. And based on the progress bar here, I did 3 of them. It looks like about 3/4 is done. So I'm hoping this is the last one. Okay, so once again, I have an improper fraction. Degree 2 over degree 2, right? The degree of the numerator is not smaller than the degree of the denominator, so it's improper. So I'm going to distribute the 2 here. I mean, I guess you could also pull the 2 out. But yeah, I'm going to distribute the 2 and do division, and then maybe I'll pull a 2 out later. We'll see. So I'll write this out. So we got this integral of, the numerator is 2 times the quantity, x squared plus 3x plus 5. And then the denominator polynomial is x squared plus 2x plus 4. So I'm going to do this. You could pull the 2 out now if you want, right? It's a constant multiple. I'm just going to do this, all right? Can't hurt to do either one. Maybe what I'm doing will take longer, but whatever, it'll still work out. So I got an improper fraction, right? Meaning my first step is going to be divide. Do long division, rewrite this fraction here as a quotient plus remainder over divisor. Quotient plus a proper fraction. All right, so numerator's going inside. That'd be, after distributing the 2, the numerator would be 2x squared plus 6x plus 10. And the denominator, the divisor on the outside, also in descending order, x squared plus 2x plus 4. All right, so we divide the lead terms. That's just 2. Multiply that term I just wrote up here by the divisor. It's 2x squared plus 4x plus 8. And then subtract all of that in the line above it. 2x squared minus 2x squared, nothing. 6x minus 4x, 2x. 10 minus 8, positive 2. And that's it, I'm done, right? I'm done with the division. This has a degree of 1, which is smaller than my divisor's degree. So now we have this integral, integral of, and I'm rewriting this fraction I started with as quotient, right, 2, plus, and then the remainder over the denominator, the remainder over the divisor, 2x plus 2 over x squared plus 2x plus 4. And this turns out to be, again, very similar to what we've seen in the last couple examples. The integral of 2, no problem, 2x. And then once again, as in the last 2 examples, this fraction here, when I'm integrating this, notice the derivative of the denominator is the numerator. X squared plus 2x plus 4. If I let that be u, then the 2x plus 2 dx would be du. You'd have du over u, natural log of u, natural log of the absolute value of u. So this is just the natural log of the absolute value of x squared plus 2x plus 4. And then, of course, plus any constant for these indefinite integrals. And there we have it. So I'll punch that in, and hopefully I'll be done with this first objective, and then we can move on to the next. 2x plus the natural log of the absolute value of x squared plus 2x plus 4. And then, of course, plus c at the end. Don't forget that plus c for an indefinite integral. Mhm. Yay, confetti coming down. All right. So first objective's done. All right, so next topic. Now, I want to do some, I can't switch to the individual objectives. Okay. I guess I misinterpreted that. I am sorry. You can switch between the objectives with the bold headings, but you can't switch to the individual objectives. So yes, I guess I could have, while doing the integration using polynomial long division, I could have switched to integration using partial fractions. I see. All right, so unfortunately, can't switch to one of these other two here. It is gonna bounce me around between these three from now on. Okay. So my apologies for earlier. I misinterpreted the switch. I didn't actually play around with it before. But yeah, so it looks like you can only switch between the bold heading objectives and not the sub-objectives or the individual objectives in those bold headings. But that's okay. All right, so now we're asked to integrate a rational function, and I think from now on we'll be working with proper fractions. Of course, if there ever is a problem with an improper fraction, you know what to do, right? You start off using long division. So integrate a rational function using partial fractions with repeated linear factors, or a quadratic factor that can't be factored, right? An irreducible quadratic. Right. So this method of partial fractions, remember what I'm trying to do is take my initial proper fraction and write it as a sum of other proper fractions by splitting up the factors of the denominator. Right. So that's a very generic way of saying that, but let me show you what I mean here, right? And of course, we'll see plenty of examples throughout the rest of this video. The rest of this video is using this method of partial fractions to integrate a proper fraction. All right, so I'll write this one out. So we have the integral of 3 over x squared times 4x plus 5. All right, so look at this. This is a proper fraction. Now, the denominator is already factored. Okay, that's what I want when I'm doing this method of partial fractions. The denominator is already completely factored. If it weren't factored already, I'd factor it myself. Yeah, so look at this. We got a proper fraction, 3 over, then the factors down here, x and x, right? This is x times x squared, and then 4x plus 5. Now, x squared Again, this is x and x again. So really what we have here is not a quadratic. I know x squared on its own you would think of as a quadratic, but it's a linear repeated x and then x again to make x squared. So they would say that we had a repeated linear here, repeated linear factors. And then the 4x plus 5 is, of course, to the first power. So this is a non-repeating linear factor still. It's 4x to the first, right? So non-repeating, oops, it's an R, non-repeating linear factor. Okay, but I just have a bunch of linear factors here. X, 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 and 4x plus 5. Right, so what we're going to do is we're going to split this up into what's called the partial fraction decomposition. Partial fraction decomposition. Now I'll be abbreviating this PFD. From now on. So what we're doing is we're splitting this up. All right, we're splitting it up into a sum of proper fractions. I want to take one proper fraction and write it as a sum of proper fractions. And the number of fractions I'm putting out there is going to be the same as the number of factors in my denominator. So there are 1, 2, 3 factors. So I'm going to have 1, 2, 3 fractions, 3 proper fractions we're going to add. All right. And here's how it works with repeats. So, x squared, we can think, so I'm going to start off with, you got x, and then one with another x. So x and then x squared. So with the repeated factors, start off with one fraction with the denominator to the first power, with that factor to the first power, and then work your way up, until you get to the power that's actually in the factorization of the denominator. So you got one with x, and then one with x and x, another x, right? And then another one with the other factor, 4x plus 5. Now, all these denominators here, if you were to find the least common denominator, it would be the original denominator. Okay, that's kind of part of this, why we're doing this here. I'm splitting it up into a sum of fractions where this is the LCD, and it'll be a lot easier to integrate with these simpler denominators than with this complicated product for a denominator. Right now up top here, remember I want these to be proper fractions. Okay, the initial fraction is a proper fraction, right? So I'd like all these to be proper fractions as well. Right? Now, if you have a linear in the denominator, in order for it to be proper, remember a proper fraction, the degree of the numerator is smaller, then the numerator needs to be a constant. And I'm going to call this first constant A. And then all the other fractions that are associated with that linear would also have constants. Right? So I know x squared is, degree 2. So you might think, oh, put a degree 1 up here. But maybe off to the side. Look at what would happen if I put a degree 1 up there. If I had something over x squared and I put a degree 1, say bx plus c, right? There's a linear polynomial with coefficients b and c. Well, couldn't you just divide each of these by x squared? You get bx over x squared and plus c over x squared. And you see here, you're just getting b over x. You're just getting another thing, another constant over x. And then a constant over x squared. And this b over x, could be absorbed, put together, and then you'd have another constant over x, It would just add to this first fraction. So when you have these repeats, right, when you have repeated factors, you're putting the same kind of stuff over those denominators, right? The same type of object. So over the x, I had a constant, and this is part of the repeat, x squared. I put another constant up there, right? So just a constant b. Right? So hopefully that made sense. I hope it did. And then this last one's not a repeated one, right? Just 4x plus 5 to the first power was showing up here, but still, I want it to be a proper fraction. And if that's a degree 1, then the numerator needs to be a constant. So again, introducing a new constant here, I'll call it c. So again, a, b, and c in this instance. So now the goal, I'm trying to get a sum of fractions here that's actually equal to my original. I want to find a, b, and c. I want to find the value of these constants. And the first thing I'm going to do is take this equation I got here, all right, where we took our original proper fraction and wrote it as a sum of other proper fractions, this partial fraction decomposition here. I'm going to multiply through by the denominator just to get rid of all the denominators. So I multiply both sides by the denominator first. So that would be the x squared, times the 4x plus 5. Now, if you do that, the whole point of that is to get rid of all the denominators, right? If I multiply this first fraction by this, everything will cancel in the denominator. You'll be left with just 3 on the left side. All right, and then this first fraction, the a over x, when I multiply it by this, one of the x's will cancel, and then I'll have a times x times 4x plus 5, right? A times x, then times 4x plus 5. All right, and then plus, and when I multiply the second fraction, the b over x squared by this, the x squareds will both x factors will cancel, and then I'll have b times the quantity 4x plus 5. And then finally, the last fraction I got here, when I multiply this c constant over 4x plus 5 by the denominator, the 4x plus 5s will go away, and then I'm left with c times x squared. All right, so what we end up with here is a polynomial equal to another polynomial. And what I want to, I'm trying to set up an identity. All right, this should be an identity, meaning that I need this to be true, right? Whatever I get here, I need this to be true for all values of x, that are allowed. Of course, you can't plug in 0 or negative 5/4 here, but so this is also going to be some sort of identity where these need to be true. This needs to be true for all values of x. Since I got rid of the denominators, let's just say for all real values of x. Now, the only way two polynomials form an identity is if they have the same coefficients. All right, the only way a polynomial is equal to another polynomial for all x, for all values, is that the coefficients are the same. The coefficients of x squared, the coefficients of x cubed, of x to the fifth, whatever, the constants. All right. So one way you can go about finding a, b, and c here is to, I'm going to actually look at how these polynomials compare. I'm going to multiply this side out here, and we'll gather all the like terms. So on the left side, I have, still 3. Now over here, if I gather the x squared terms, right, I notice the highest power on x for anything over here is going to be x squared. We'd have, 4a. I'll just write it out first and then we'll gather the terms. We have 4ax squared plus 5ax to the first. And then here distributing the b, you got plus 4b times x, and then plus 5b, and that would just be a constant, right? There's no x there. And then this last term is an x squared term. So now I'm going to gather, all the terms, and on the left side I'm going to do this too. You got x squared terms, x terms, and constants over here on the right. So over here on the left you got 0x squared, right? There's no x squared term, plus 0x to the first, right? No x term, and then plus 3, right? That's your constant 3. So that's the left side polynomial. And on the right side, when I gather the terms together, right, here's the x squared terms, combine them. You have 4a plus c x squared. Right. So the coefficient of x squared on the right side is 4a plus c. Plus, and then the x terms together, right? There's an x term, there's an x term. Gather those up, factor the x out. You got 5a plus 4b, right, for the coefficient of x. And then the only term left is our 5b here, and that would be the constant term. You could put in parentheses if you want, but that's our constant term, and I've gathered all the like terms together. Like I said, this needs to be an identity. This needs to be true for all x, and I said it already, right? Polynomials form an identity only when their coefficients are equivalent. So what I'm going to do now is equate the coefficients. So the coefficients of x squared need to be the same, right? So 4a plus c needs to be the same as 0. And what we're doing here is we're actually setting up a system. We're going to have a system of 3 equations with these 3 unknowns, a, b, and c. So we got 4a plus c, right? That must be 0. And then the coefficient of x, they need to be the same as well for this to be an identity. So 5a plus 4b must also be 0. And then your constant terms. Over here I have 5b as the constant, and then over here I have 3. So 5b must be 3. All right, and then I solve for a, b, and c. I can solve this system now pretty easily. B from the last line, right? B must be 3/5. Okay, so I got the value of b. Wonderful. And then from here, 5a plus 4 times, 3/5 plus 12/5. Right? I know that b is 3/5, so that's 12/5 there. Must be 0. And then this would lead me to a must be, and you subtract 12/5, divide by 5 or multiply by a fifth, that'd be negative 12 25ths. Negative 12 25ths. Right, so there's the value of a. And then c, right, from the top equation, the value of c has to be negative 4 times a. Right, subtracting 4a from both sides there. And so the value of c must be negative 4 times a, that'd be positive 48 25ths. Positive 48 25ths. And there we have it. All right, the value of a, b, and c. All right, now I'm going to show you, because we might see some bigger systems later. I'm going to show you a way to use what's called an augmented matrix. All right, you may have seen this if you've taken a linear algebra course, or perhaps you even saw this in an algebra course where they showed you how to solve, 2x2 or 3x3 systems. But I'm going to show you a little shortcut here not a shortcut, but a way to use a calculator. If I didn't have a calculator, right, I'd have to be doing this. Or I could do what I'm about to show you by hand, but I'd rather not. So what I'm going to do here, I'm going to go to Desmos. Sorry, didn't mean to have that new stuff up though. Desmos.com. And then under Math Tools, you see this matrix calculator. Matrix calculator. I'm going to create a new matrix. And the number of rows is the number of equations, right? There were 3 equations, so I want 3 rows. And the number of columns, right? The vertical columns is the number of variables plus 1, right? Plus your other side, the numbers on the other side of the equal signs. Now there were 3 variables, so ABC, and then add 1 more. Right? So we got a 3 by 4 matrix here. Now, in these columns, down the first column, I enter the coefficients of A. So 4, 5, and there was 0A in the last equation. Right? Down the second column, put the coefficients of my second unknown, which was B. Well, there was 0B in the first equation, 4B in the second equation, and 5B in the third equation. And then down the third column, I'll put the coefficients of my third variable, the C. Well, there was only one C in the first equation I wrote. There were no C's in the other two, so 0 and 0. Right, and then this last column here is the numbers on the other side of the equal signs, right? The coefficients from the other side of the equation. So we had, 4A plus C equals 0, so I put 0 there. Second equation was 5A plus 4B equals 0, so I put 0 at the end there. And the last equation was 5B equals 3, so I'm putting 3 there. So there, I've got this matrix. And then what I'm going to do, see in the lower left corner here, there's this thing called RREF. This is called Reduced Row Echelon Form. I'm going to hit that button, RREF, and you can't see it, it's off screen here. It says RREF, and then what matrix? Well, the previous matrix had a name of A, so I'll put A, whatever I called the matrix earlier. This matrix up here, the 3 by 4, 3 row, 4 column matrix I made was called A. Put it into this RREF form, and then look at this over here. Now, this button says convert to fractions, and look at these fractions. We have 1A plus 0B plus 0C equals negative 12/25, right? So A must be negative 12/25. That's what I had on my paper earlier. Second row, no A, 1B, no C, so B must be 3/5. But again, that's what I had in my paper earlier. And then the third row, no A, no B, 1C, so C must be 48/25, and that's exactly what I got earlier on my paper. Okay, so if a system is big or I don't feel like working it out by hand in the rest of the video, I will be going to that matrix calculator and doing this. All right. All right, so now finally, what are we doing with these? So remember, it's been a while already, right? What I'm doing with this A, B, and C, I'm putting it in this partial fraction decomposition, right? So now we're going to rewrite our original proper fraction as a sum of these proper fractions, where A is, negative 12/25, and B is 3/5, and C is 48/25. And we'll rewrite our integral. All right, so here's the integral rewritten. So this integral I started with now is this, the integral of And I'm rewriting this proper fraction as this sum. And A is negative 12/25 over x, right, over x, plus B, right, we found B was positive 3/5 over x squared, or 3/5 times, x to the negative second. So I can use the power rule to integrate this, right, because x to the negative second is fine. There's no natural logs here. And then lastly, plus, C was 48/25 over the linear, right, 4x plus 5 dx, right? So I've just rewritten this proper fraction as a sum of, simpler proper fractions, right? All these, what they call partial fractions. And now I should be able to easily go through and integrate these, right? So this first term is negative 12/25 times the natural log of the absolute value of, and that's just 1x, so I would divide by 1 afterwards, but that doesn't do anything. Now remember, this is x to the negative second. So it'd be x to the negative first, so over x, and then times negative 1. So I'd have, minus 3/5, so minus, let's say, 3 over 5x, right? Because 3/5 over x would be 3 over 5x, same thing. And you can, again, differentiate this. You'd be positive 3/5 times x to the negative 2. That's this thing up here. You differentiate. Then lastly, plus, now we have 48/25. We'd be, I'm dividing by a linear here, so you're going to do the natural log of 4x plus 5, the absolute value of 4x plus 5. But remember, there's this 4 in front of the x. So I'd multiply by a quarter. So 48/25, times 1/4, that's 12/25, right? 4 goes into the 48 12 times. So I'd end up with 12/25 there, times the natural log of the absolute value of 4x plus 5. And then I'm done with all my integrals now. And add some constant, right? Plus C. So this is what I'm going to be typing in. Now you could put these logs together, factor out the 12/25, and then take that log. We could combine logs, do a different a log of a quotient, but I'm just going to type this. All right. So we ended up with negative 12/25 times the natural log of the absolute value of x minus 3 over 5x. And then plus 12/25 times the natural log of the absolute value of 4x plus 5. Get out of here, plus any constant, and this should be good. Great. Yeah, so they wrote it a little differently. It's really no different. All right, so again, you may have something that looks different than theirs, but as long as they're equivalent, they'll be accepted. All right. All right. Again, they describe to you how to write out the partial fraction decomposition in each case where you have non-repeating linear factors, repeating linear factors, non-repeating quadratic, irreducible quadratic factors in your denominator. So those will have linears up top, right, to be proper. And then your repeating quadratic factors, repeating irreducible quadratic. So take a look at these again. All this, you can pause right now, read through those, but those are I'm going to keep referring back to that or doing those processes as we go through all these examples. Great. All right, so yes, here, integrate a function using partial fractions in applications. All right, so this is your volume of a solid of revolution, area between two curves, arc length, surface area of revolution. All right, that kind of stuff that we saw in all the chapter 2 sections. So they're bringing those back here, right? And the integrals that get set up here, you know, should be able to be done through this method of partial fraction decomposition, or just partial fractions. All right, so we're asked to find the volume of the solid generated by revolving the region enclosed by the graph of the function f of x equals 6 over x squared plus 9x plus 18, and the x-axis over the interval 0, 1, and revolving this region about the y-axis. And they would like an exact answer. All right, so we need to actually integrate. Now, if they ask you to round an answer to so many decimal places, then you could enter your integral, your definite integral, into a calculator and just get the approximation that way. All right, so I'll draw this region. So we have f, they're giving us this function f of x equals 6 divided by, and then x squared plus 9x plus 18. And then we're on the interval just from 0 to 1. All right, now the graph of this, now if I were to factor the denominator here, you could see where it's undefined. X squared plus 9x plus 18, that's x plus 6, or x plus 3 times x plus 6. All right, that multiplies to be x squared plus 9x plus 18. So the graph of this thing, it has asymptotes at -6 and -3. All right, you couldn't plug these values in for x. And, the value of the function over here, from 0 to 1, right? We're only looking at the interval from 0 to 1 would be positive. When x is 0, you'd get 6/18, you get, 1/3. So I'm really not worried about these asymptotes here. So I'm just graphing it over here. It's going to be positive values. And when x is 1, you get 4 times 7, you get 6/28, right? Which would be less than a third, right? Because 6/18 is a third, and then you raise it. If you make the denominator bigger, 6/28, you make the number smaller. So 6/28 or 3/14 for the output there. And be part of this graph over this region would look like that. Right? Just this little piece of, there's more to the graph, of course, but this is all they want, right? Just over the interval from 0 to 1, over the x-axis. So this region here is the region they're talking about. Now, they don't want the area of this region. What they want is if I were to revolve this region around the y-axis. So that would create like a little, almost like a solid, like circus tent type thing, right? But it's solid, right? We're finding it's all filled in, not hollow. So we're finding the volume of this shape here. Now, I could do discs, right? Take slices perpendicular to the line, to the y-axis. But it looks like it would be a lot easier to do this with cylindrical shells, this volume, right? So I take a slice that's vertical. I take a slice parallel to the y-axis. That would be for some x value between 0 and 1 for the thickness of dx. And then I'd get a shell. Right? Again, a shell is kind of like just a little thin rolled up piece of paper. Right? Really thin walls here. The thickness is called dx, and running through the hole in the middle is the line we rotated around, right? The y-axis. The height would just be the y coordinate, the height of the rectangle here, which is y to the top minus y to the bottom, which is just y on top here. So I'll just say that's f of x, right? I'll write this up later. And then the radius we need as well, right? Radius is the distance from the line of rotation to the rectangle, which is just in terms of x, it's just x. That would just be the x coordinate at my rectangle, at my slice. And remember the volume of a shell right, is the circumference of the paper times the height times the thickness. So 2 pi x, right, 2 pi x times the height times f of x, which I'll write up the fraction later, and then times the thickness dx. And we're doing this, we're adding all these shell volumes up for I'd be doing this for every x value from 0 to 1. All right, so I'll write up the integral that gives me my total volume here on the next page. So the volume of that filled in solid circus tent would be the integral, right, we're doing this from x equals 0 to 1 of these shell volumes. So 2 pi x times, and then f of x, right, was this fraction 6 over, and I'm going to write the denominator in the factored form because I'm going to be using this method of partial fractions. All right, so I want the denominator in factored form. So 6 over, and then the factored version of the denominator was x plus 3 times x plus 6. All right, and then times your thickness dx. Okay. So I'm going to pull the 2 pi out. All right, so we got 2 pi. Actually, I'm going to pull 12 pi out. Because you got 2 pi times 6 up here. Okay. So I'm going to pull 12 pi outside. And then we have the integral from x equals 0 to 1. And if I pull 12 pi outside, you just have x in the numerator now, divided by this, x plus 3 times x plus 6 down here. And then, of course, your differential, right, times the thickness times dx. So look, I have an integral involving a rational function, and this rational function is proper. Right. Now, if it's a proper fraction, right, the degree of the numerator is 1, the degree would be 2 in the denominator, right? That would be x squared plus 9x plus 18, as you saw initially. So with these proper fractions, I'm going to try, first, which I've already done, but factor the denominator completely. Factor the denominator completely, which is already done here. I've already done this. All right, so we have x over x plus 3 times x plus 6. Now notice my factors here are both non-repeating linears, right? These are both linear to the first power. So again, like I was saying earlier, we're going to do the PFD over here, right? Partial fraction decomposition. I want to take my initial proper fraction and write it as a sum of proper fractions with each of the factors in my denominator showing up. Now there are 2 factors here, so I'm going to have 2 of these fractions. Fraction plus fraction, right? Again, the number of fractions in my PFD is going to be the same as the number of factors I have in the denominator, right? You saw that last example with the x squared and the 4x plus 5. That was x and 4x plus 5, so I had 3 fractions, right? Here I have 2 factors in the denominator, x plus 3, x plus 6. And since they're not repeating, those are the only denominators here. You got x plus 3 of the first, and there's no x plus 3 squared or cubed or anything. It wasn't a repeating factor. And then the other one's going to have x plus 6 to the first. And again, I'm not adding more with squared and cubed, and it's not repeating. And then I want to write a proper fraction as a sum of proper fractions, right? Now these are, we have linears over here in the denominator, so I'm putting constants, a and b, right? Just a and b. Constants in the numerator. All right, so now I want to find a and b. I got this identity here. I want this to be an identity, true for all values except for, -3 and 6, -6. Multiply through by the numerator, right? So x must be the same as, a times x plus 6. All right, if I multiply this fraction by that denominator, the x plus 3's will cancel, right? So I'll have a times x plus 6 plus, and then b And this fraction times this denominator, the x plus 6's would cancel. You'd have b times x plus 3. All right, and again, I'm going to say, hey, this is an identity, polynomial equal to polynomial. So the coefficients have got to be the same. Right? So I'm going to gather all this stuff over here. So we got x equals, you know, I'm going to put them all together right now. ax plus bx, right? So that'd be a plus b times x. And then the constant term, you have 6a plus 3b. 6a plus 3b would be the constant term. Now, if I equate these coefficients, I'll get a pretty small system, right? There'd be only two equations. There's only two variables here. So the coefficients of x need to be the same, right? A plus b needs to be 1, right? The coefficient of x on the other side is 1. And then the constant term, 6a plus 3b, that's got to be 0. There's no constant term on the other side. Now, if I divided everything by 3 here, this is the same as 2a plus b must also be 0, right? And that tells me that b must be the same as negative 2a. And if b is negative 2a, a plus negative 2a would be negative 1a, must be 1. And so a must be negative 1. And if a is negative 1, from the b equals negative 2a thing, b must be positive 2. Right. Now, another thing you might want to try. So far the last couple examples, when I was doing these partial fraction decomposition and finding the values of the unknown constants, I multiplied everything out and then I equated the coefficients, got a system. Another thing you could try is back up here when after multiplying through by the denominator, we could take this statement we have here and I could just try to find a and b by plugging in. Remember, these could be true for any x. I set up an identity here. So I could do this. I could plug in some values for x until I figure out what a and b are. Plug in values until you know a and b, until you find the constants. And with these linear factors, a very clever thing to plug in would be anything that makes your factors 0. That'll make certain terms disappear. So like say I wanted to solve for a. Well, to get rid of this b term, I would just need to replace x with negative 3. Right? Negative 3 plus 3 is 0, so I'll do that. So in this equation up here, this identity, I replace x with negative 3. On the left side, we'd have negative 3. And on the right side, we'd have, a times negative 3 plus 6 plus b times negative 3 plus 3. But that's just 0. So that term is gone. We have negative 3 equal positive 3a. And then dividing both sides by 3, we get a equals negative 1. This is exactly what I found earlier, right, when I equated the coefficients and solved the system. That a was negative 1. So now so I've got a now. So I could go back up here and replace a with negative 1. So just keep that in mind. Any other value I plug in for x, a has to be negative 1. Well, if I want b, then you can plug in any other value you wish. That should be an identity. Work for any x, any real x. So I could plug in 0. I got 0 over here. Remember, a is -1. So this would be 6 times -1 would be -6. And 3b, you'd get, now this isn't the best choice. I'll show you the best choice in a second. But if x were 0, right, you'd have 0 on the left. Remembering that a is -1. This would be -1 times 0 plus 6. That'd be -6. And then x is 0, so 3b plus 3b. If I solve this for b, a would add 6 divided by 3. B must be +2, which is, again, what I found earlier, when equating coefficients. But of course, the best choice here, and you don't always have, I just showed you don't always have to make the best choice, but it'll be a lot faster if you do. You might have to plug in multiple values until you figure out what the value of a certain constant is. But the best choice here, if I wanted to find b, just plug in -6 for x, right? That'll make this a term disappear. All right, if x were -6, on the left side you'd have x, so -6. And then on the right side, a times 0 plus, and then b times, -6 plus 3 would be -3. You'd have -3b over here. And then that leads me to b equals +2 as well, dividing both sides by -3. So yeah, so this is an alternate way of doing things. Finding these constants, you can recognize you have an identity, right? So this should be true for all x. And then start plugging in values of x until you figure out what the constants need to be. And some values will be better to choose than others. Usually you want to make things equal 0 so that certain terms disappear. All right. Well, now I have these values. Wonderful. We can do our integral. So I'm replacing a with -1 and b with +2. So I'm going to do this now. All right, I'm just going to ignore the limits for now. All right, ignore 0 and 1 for now. I'll just write the integral up. So now we have, and then we'll multiply with a 12 pi at the end. All right, so I'm ignoring this 12 pi and the 1 and 0. So this fraction here, this x over x plus 3 times x plus 6, remember, now I'm writing it this way as this sum, where a is -1, so -1 over x plus 3, plus, and then b is +2 we saw, so 2 over x plus 6. We're doing this integral now, which is a lot easier. And so the antiderivative is easy, right? These are linears with coefficients of 1 on the x. So this is just negative, natural log of the absolute value of x plus 3 plus 2 times the natural log of the absolute value of x plus 6. And now I'll put the limits back. All right, we're going to multiply this by 12 pi when we're done. I had the 12 pi outside earlier. And now I'm going to go, we're going x equals 0 to x equals 1. So I plug in 1 for x, I plug in 0 for x, and we subtract. So this is 12 pi times, now when I plug in 1, we have negative natural log of 4. I don't need the absolute values on that. That's a positive number. Plus 2 times the natural log of 7. Again, don't need absolute values around that. There's the value of this thing when x equals 1. And then I'm going to subtract from that, right, the value of the expression when x is 0, which would be negative natural log of just 3, right? No need for absolute values. It's already positive. And then plus 2 times the natural log of, 0 plus 6, just 6. There we go. And I'll distribute the negative here. And then I'm going to actually put all these together, right? Remember, if you have a bunch of logs being added and subtracted, this is great. This is fine. You could type all this, but if you have a bunch of logs being added and subtracted, you get negative natural log of 4 here plus, remember numbers in front, you can put in as powers. This would be the natural log of 7 squared, or 49. Then plus the natural log of 3, and then minus, and then putting the 2 in here, 6 squared, you got minus the natural log of 36. And then if I put all these together using my properties of logs, we'd have a log of, now the stuff with the positive coefficients would be in the numerators, they'd be multiplied in the numerator, 49 times 3. And the stuff with the negative, the minuses, those would you'd have that product in the denominator, 4 times 36 in the denominator. And then I can simplify this a tad. 3 goes into 36 12 times. Right? And so we have the natural log of 49/48, right? Which is bigger than 1, so that'll be a positive value. And then times 12 pi, right? Don't forget the 12 pi here. There's our cubic units, right? There's the volume of that solid circus tent shape that I was drawing up earlier. But like I said, you can type out what I had here times 12 pi, and that'd be fine too. I'm just using properties of logarithms to put all this stuff together. So I have less typing here. Now that, again, they want an exact answer. So 12 times pi, right? Then times the natural log of 49, 48, 48, 48. And that should be good. Great. Oh, and they actually did put it all together. Wonderful. But if you typed out, like I said, if you typed out the entire thing I had earlier without putting it all together with properties of logarithms, right, it still should have given it to you because they are equivalent numbers. Great. And once again, all the how to write out the partial fraction decompositions in the 4 different cases here. All right. Okay, so now we're in a new objective. Integrate a rational function using partial fractions with non-repeated linear factors. So we actually just saw this. All right, the example before this had, x plus 3 to the first and x plus 6 to the first in the denominator, non-repeating linear factors. So this will be very similar, but instead of having 2 linear factors in the denominator, it looks like we're going to have 3 because this is a cubic function in the denominator. All right, so let's write this out. Got the integral of a proper fraction again, right? So do this, factor the denominator completely and try to write out the partial fraction decomposition. So negative 3x minus 4 over cubed plus 11x squared plus 28x, and then you got your bx over there. So again, I'm going to take a look at the fraction on its own. We have negative 3x minus 4 in the numerator, and if it's a proper fraction, the first thing I'm going to want to do is factor the denominator completely. Every single one of these terms has x in common, right? So there's x to the first, right? A linear to the first, a non-repeating linear factor. Times, and then when you remove x, you've got x squared plus 11x plus 28. That would factor to x plus 4 times x plus 7. Those make x squared plus 11x plus 28. And then times the x would be x cubed plus 11x squared plus 28x. Okay. So yeah, so I'm in that case again where all my factors down here are non-repeating and linear. And there are 3 of them, right? So when I do the partial fraction decomposition over here, I'm going to have a sum of 3 fractions. three proper fractions. And, since they're non-repeating, those are the only factors that are going to show up in these denominators. Just, one with x, and again, it's non-repeating, so there's no x squared or x cubed one, right? Like there was in that one example a while back now. One with the factor of, x plus 4 in the denominator, and the other one with the factor of x plus 7. And if I need, if I have linears, right? These are all coming from linears. So in order to be proper, we need just constants above. Again, I'll call them A, B, and C. All right, so what I'm going to do is now to try to find the A, B, and C, multiply by the denominator. So we got negative 3x minus 4 on the left. When I multiply this fraction by the denominator, the x's would cancel. I have A times x plus 4 times x plus 7. Plus, and then the next fraction, when I multiply it by the denominator, the x plus 4's will cancel. And then I'd have b times x plus 7. And then the last fraction here, if I multiply by the denominator, you'd have x plus 7's canceling. And you'd have c times x plus 4. Okay. Now I could do like I was doing in previous examples where I multiply all this out and then equate the coefficients. But I'm telling you, like with the last example I showed you, when you have these linear factors, it's very easy to just, we have an identity here. I could just plug in some values of x, right? This should be true for any value of x I want. So I'll plug in some clever values. If I want a, to get rid of the b and the c terms, I just need to replace x with 0. So I'm going to do that. I have x be 0 to start. Now, if x is 0, the left side would be negative 4. And the right side, again, the b and c terms would disappear. And I'd have 0 plus 4 times 0 plus 7, 4 times 7, 28a. And so now I can solve for a. A would be negative 4/28, or negative 1/7. All right, so there's the value of a. I'll put that here. And if I want b, to get rid of the a term and the c term, I would have to replace x with negative 4. So let's do that. A clever substitution here would be negative 4. Now, if x is negative 4, the left side would be positive. Negative 3 times negative 4 is positive 12, minus 4 is 8. The left side would be 8. On the right side, you got no a, no c, and then negative 4 times negative 4 plus 7. So negative 4 times, 3, negative 12b. And solving this for b, divide by negative 12b, would be negative 4/12, or negative 1/3. So there's the value of b. I'm going to put that here in the PFD. And then finally, if I want to find c, I need to replace x with negative 7, right? That'll get rid of the a and the b terms. Now, if I replace x with negative 7, this would be 21, minus 4, be 17 on the left side. And then no a, no b, and then negative 7 times negative 7 plus 4. So negative 7 times negative 3, that'd be positive 21c. And then just simply divide by 21. So c is 17/21. All right, now I'll put that here in the PFD. So keeping these in mind, we can now rewrite our integral as the integral of a sum of proper fractions, right? So we have the integral of, and then instead of that, that negative 3x minus 4 over x cubed plus 11x squared plus 28x, right now I can write it as this sum, as negative 1/7 for just x, plus, and then negative 1/3 at the b, over x plus 4. And then plus, and then c is, 17 21sts over x plus 7. And take this term by term, and these are all something over a linear, so these are all involved natural logs. So we get negative 1/7. Pull that out times just the natural log of the absolute value of x. And then, pull out the negative 1/3 in the next integral if I integrate the next term. Minus 1/3 times the natural log of the absolute value of x plus 4. And then the last one, pull out the 17 21sts plus 17 21st times the natural log of the absolute value of x plus 7. And of course, indefinite integral, right, plus some constant. This is what I'm going to be typing. Now, of course, you could, if you wanted, because you got a sum of a bunch of logs here, difference of a bunch of logs. You could put all these together as a single log if you want with properties of logs, but I'm just going to type this. All right. So we got negative 1/7 times the natural log of the absolute value of x. After that, minus 1/3 times the natural log of the absolute value of x plus 4. And finally, plus 17 21sts times the natural log of the absolute value of x plus 7. And then after all that, right, plus some constant, it should be good. Oh, did I make a mistake calculating my constants? All right, I am going to go and check that out. And I'll be back when I figure out what went wrong. I'm so sorry. Figured out where I went wrong here. Back when I plugged in -7, you probably caught it, but you can't scream at the screen and have me hear it. My apologies. When I plugged in -7, right, you had no A, no B. -7 times -7 plus 4, -3. Now that is positive 21. All right, hold on. Something went wrong somewhere. Okay, I really see it now. Sorry. This is where it went wrong. Next is -4. That's 12 minus 4. That's not 4. That's 8. I put 4 for some reason. Probably because I said 4 last. And then I divide by -12, -8 over 12 is -2/3. So that changes this to -2/3 over x plus 4. And this to -2/3 times the natural log of x plus 4. So it's a good thing they give you one more shot at these, right? So I don't lose any progress. I can still get this correct. Just change this here to a -2/3 times the natural log of absolute value of x plus 4, and everything else should be good. Wonderful. Again, I apologize for that. The error was fixed, and we can move on. This is why you check your solutions, folks. But again, I don't want to have this video be 5 hours long. All right. Okay. Moving on. All right, so here's integrate a rational function using partial fractions with non-repeated linear factors. So it's the same objective, right, where we have the non-repeating linear factors. So evaluate the following integral using partial fractions, right? So this one here, the way it starts is like all these trig functions, but after making a nice u substitution, you're going to see I can turn this into an integral of a rational function. Right? So some of these may not look like a rational, but after a nice simple u sub, you can turn it into a rational and then go from there with the partial fractions method. All right, so let me write this up. So we got the integral of They have the minus sign out front here. I'm just going to put it in the numerator. -2 times the sine of x in the numerator, divided by, and then 4 times the cosine of x, squared, cosine squared x, plus 2 times cosine x, and then your dx over here. Okay. So again, at the moment, it's some trig integral, not a rational function, not a polynomial over a polynomial. But if I were to make the following sub, isn't the derivative of cosine negative sine, right? So if I made this sub, say I let u be just cosine. Everywhere there's a cosine of x, I'm going to replace it with u. And then du would be negative sine of x times dx. And I'm seeing that up here, negative sine of x times dx, right? All those together make du. And then there's a u here, right? That'll become u squared. And there's a cosine here, that'll become u. So you see when I'm done making this substitution, we'll now have a rational function, a polynomial over a polynomial, but in this new variable called u. So up top, I just have 2 du. So 2, I'll put the du at the end here. Right? That's all there is at the top. And then the bottom, we have 4, u squared plus 2u. And do you see how now we have a rational function in this variable u? Right? It's rational in u, polynomial in u divided by a polynomial in u. All right, and one more thing I want to do here is I noticed that both these have 2 in common. Factor that out, cancel the 2. So I'm also gonna factor the denominator. All right, let's just skip ahead. If I pull 2 out of here, 2's will cancel. You got 1 in the numerator now. And if I factor a 2 out of here, there's also a u in common. I pull a u out. And if I pull a u out and a 2, or if I pull a 2 and a u out, you'd have 2u plus 1 as the other factor, right? So I factored out 2u, cancel the 2's. All right, so I got this now. And look at the fraction. This is a proper fraction, right? The degree of the numerator is 0, the degree of the denominator is 2. And I factored the denominator to these non-repeating linears, right? They both got u to the first power and they're to the first, right? It's u to the first, 2u plus 1 to the first, non-repeating. So I'm going to do the PFD down here. All right, so this fraction, this 1 over u times 2u plus 1 proper fraction, I should, based on what we've been seeing in all the other problems, right, I should be able to rewrite this as a sum of, there are 2 factors in the denominator. So a sum of 2 fractions. One with a denominator of u, the other with a denominator of 2u plus 1. Right, and again, there's no higher powers of these going on because we don't have repeated factors. All right, and then being linear, remain proper fractions, right? I would need just up to a constant in the numerators, right? Just then these constants a and b. Then I'll multiply through by the denominator. We have 1 on the left. First fraction, the u's would cancel. I'd have a times 2u plus 1. Plus, and then the second fraction, when I multiply by the denominator, the 2u plus 1's cancel. I'd have just b times u. And then I'll do the same thing, hopefully not make a mistake with my arithmetic like I did with the last example. My apologies once again for that, but this should be an identity true for any value of u. If I want to solve for a, I'm going to have u be 0. And if u is 0, right, you got 1 on the left all the time, it's just 1. And if u is 0, this would be 0 plus 1, this is just a. So the value of a is 1. And if I want to find b, I need to replace u with -1/2. I could plug it in. I could plug anything I want, right? I know that a is 1 now. I could plug in something else if I wanted, but if I want to get rid of this 2u plus 1 factor, make it 0, let u be negative 1/2. And if that's the case, again, you got 1 on the left all the time. This is now 0a, and then you got, minus 1/2 b, and then multiply by negative 2. We got b must be negative 2. Okay, again, double checking my thoughts here. I don't want to have another arithmetic mistake like I did with the last example. All right, so great. Now I got them. So we can write our integral now. This integral with the u's in it, I can rewrite it using my partial fraction decomposition, my PFD. This is now the integral of, and then instead of this fraction I had up here, a over u, 1 over u, and then plus, and then b over 2u plus 1, so this negative 2 over 2u plus 1, and then we have the du. And these are nice simple integrals to take, right? We're over linears. Now this one, the linear has a coefficient of 2. So when I do the natural log of this, I'm also going to have to multiply by a half, right, to counteract the chain rule. But we have this is the natural log of the absolute value of u, and then minus 2 times the natural log of the absolute value of 2u plus 1. Remember, I said I also had to multiply by a half here, so that'll make this negative 1. And then remember what u was way back, right? We got to go back to the original variable. U was cosine x. Right? I said earlier I had u replace cosine x. So I'm going to go back to the original variable. So our final result here is the natural log of the absolute value of the cosine of x, then minus 1 times the natural log of the absolute value of 2 cosine x plus 1. All right, and I'm done integrating. It's an indefinite integral, so I throw on plus any constant there, and here we go. Again, I probably should check my work, but I'm pretty sure I didn't make any arithmetic mistakes this time. So this is what I'll punch in. So we have the natural log of the absolute value of the cosine of x. We can get out of there. Next, minus the natural log of the absolute value of 2 cosine of x plus 1 all inside the absolute value there, and then plus any constant, and we should be good. Wonderful. Okay. All right, so moving on here. All right, so another application one where it looks like another volume of the solid generating by revolving this region just from 0 to 5, though, about the y-axis. So if you go back to the first example from this objective, this is the same problem, but with different limits of integration. So I'm going to be integrating from x equals 0 to x equals 5 and doing cylindrical shells where the volume is going to be 2 pi x times this f of x dx. All right, so I'm just going to set up the integral here. If you want to draw it out, fine, but I'm just going to set up the integral, right, and we'll do it. But if you want to go back to that first example from this objective, right, using applications, please do and see how I set it up there. But this is pretty much the exact same thing with a different function and a different interval. All right, so the volume in question here is going to be the following. We'll be integrating, adding up all these cylindrical shell volumes from x equals 0 to x equals 5 this time of 2 pi x, right? X would be the radius in terms of x times, and then the f of x, the height of the shells, right, would be 4 over x squared plus 7x plus 10 was the function given. And then times, the thickness of the shells, right, the thickness of the rolled up piece of paper, dx. Okay, so I'm going to do some stuff here. Pull out you have 2 pi times 4. I'm going to pull 8 pi out of this. And then we have the integral from 0 to 5 and then if I pull the 8 pi out, you just have x in the numerator. And just x. And here's where I'll factor the denominator completely right now, because I'm going to have another proper fraction, proper rational function. X squared plus 7x plus 10. That's nicely factored, right, to x plus 2 times x plus 5 dx. Okay, so this x over x plus 2 times x plus 5, proper fraction. I should be able to rewrite this now as a sum of other proper fractions, where the number of fractions is going to be the same as the number of factors, right? And none of them are repeating. None of these are to the second power or higher, you know? So here's my partial fraction decomposition, PFD over here. I got one of these with the factor x plus 2 in the denominator, plus another one with x plus 5. And again, being linears, to keep these proper, we only need to go up to a constant. And so again, I'll call these constants a and b. We'll find a and b now, create a nice polynomial identity. I'm going to multiply through by the denominator. We have x over here, a times x plus 5 for the first fraction, right? The x plus 2's would cancel, plus, and then b times x plus 2 for the second one, right? The x plus 5's would cancel. Now, if I want to find a, right, we need x to be -2. Now, if x is -2, you know, the left side would be -2, and then -2 plus 5 is +3. We'd have 3a. All right, so the value of a would be -2/3. And if I want to find b, I need x to be -5. So left side, -5. And then the right side, you got no a. And then -5 plus 2 is -3. Right? So -3b. And dividing both sides by -3, +5/3 for b. Okay, so I got the a and b. All right, so now I can rewrite my integral here. You know what, just to save a little time, we'll be integrating this -2/3 over x plus 2, and then the b is +5/3 over x plus 5, right? So I'm just going to jump to the integral right now. So our integral would be, -2/3 times the natural log of the absolute value of x plus 2 plus 5/3 times the natural log of the absolute value of x plus 5. Right, and we're evaluating this from x equals 0 to 5, and then this gets multiplied by 8 pi afterwards. Okay, something else I'm noticing is that, both of these have a third in common. So I'll pull that out. You got 8 pi over 3. So let's do this. Let's pull the third out. And now I'll evaluate this at 5 and at 0 and subtract. So 8 pi over 3 times, and then the value of this thing at 5, -2 times the natural log of 7, plus 5 times the natural log of 10. When I plug in 5 here and here. So that's the value at 5, minus, and then the value at 0. We have -2 times the natural log of 2, and then plus 5 times the natural log of 5. And I'm going to be distributing the negative here. We're subtracting all that. And when I put all this stuff together, right, this is negative natural log of 7 squared, right, 49. And plus the natural log of 10 to the 5th power, which would be 2 to the 5th times 5 to the 5th, and then plus the natural log of 2 squared minus, the natural log of 5 to the 5th. Putting all these together, times 8 pi over 3, we get the natural log of, again, the stuff with the positive coefficients would go in the numerator. You have 10 to the 5th, 2 to the 5th, times 5 to the 5th, times 2 squared, right? That's 10 to the 5th. And so really we have 2 to the 7th in the numerator. And then the stuff with the negative, the minuses would be, that product would be in the denominator. You got 5 to the 5th times 7 squared. So the 5 to the 5ths would go away. And I'm left with, 2 to the 7th, which I know 2 to the 5th is 32. So 64, 128 over 49. This is the natural log of 128 49ths. All that put together. And then don't forget the 8 pi over 3 outside. And this would be, cubic units, right? The volume. This is what I'm going to be entering here. 8 pi over 3 times the natural log of 128 49. 49ths, not 29ths. 128 49 cubic unit. Wonderful. All right. Next. Okay, this one this one I see is going to have an irreducible quadratic factor in the denominator. Integrate a rational function using partial fractions with repeated linear factors or a quadratic factor that can't be factored any further, an irreducible quadratic. All right, so write that out. All right, so we have the integral of 4 over x cubed minus 64. Now, x cubed minus 64 is a difference of cubes, x cubed minus 4 cubed. So I can factor that to a linear, just x minus 4, times a quadratic that can't be factored more, x squared plus 4x plus 4 squared plus 16. All right, so hopefully you recall how to factor differences of cubes. I'm not writing that up here. And yeah, this can't be factored over the integers any further, right? This has no integer solutions. Integers are zeros. It has imaginary zeros, complex zeros, right? Could be factored over the complex numbers, but not over the integers. When we talk about factoring here, we're talking about factoring so that you still have integers as coefficients. Anyway, so now I've got two factors. So again, when I go to write the GFD, I should have two fractions, the sum of two fractions. And one of these will have this linear, and it's to the first power, so there's not more of them, right? Remember, when we have repeats, we just keep adding to the power. And the other one is this irreducible quadratic, right? Again, I'll write that down. We haven't seen that yet in this video. Here's an irreducible quadratic. So there's another one with this quadratic factor, x squared plus 4x plus 16. Okay, now these need to be proper fractions. If you have a linear or some power of a linear, if there was x minus 4 or x minus 4 squared, x minus 4 cubed, if you have a linear or some power of a linear in the denominator, you only need to have a constant up top. So just say a. But if you have a quadratic, or any power of a quadratic, right? So if I had x squared plus 4x plus 16 squared or cubed to the fourth, but if you have something involving a quadratic that can't be factored in your denominator, the numerator could be up to a linear and it would still be proper, right? This is a degree 2. The numerator could be a degree 1. So you'll see this, b, so some constant b times x, so the variable x is coming in here, plus c. So with these quadratics in the denominator, or powers of quadratics in the denominator, you're going to have a linear in the numerator. Whereas if you have powers of linears in the denominator, you have, constants. We've seen the constants before. I don't need to write this, but you have constants in the numerator, okay? Linears, constants, all right. And then I'm doing this the same way I've been doing, right? I want to find A and B and C, and then I'll split up our integral. So multiplying by the denominator. If I multiply by the denominator, right, the left side is just 4. On the right side, you'd have A, multiplied by this x squared plus 4x plus 16. All right. Then plus, the second fraction, the x squared plus 4x plus 16 would cancel and it'd have the x minus 4. So it's this whole thing though, right? Now the numerator, this linear, has multiple terms. So this whole thing, bx plus c times, and then the x minus 4. All right. So you could do the thing where you multiply everything out, get, polynomial equal polynomial identity, and then set the coefficients equal to each other, which I'll do that. All right. So if I distribute the a here, and then over here I'd have to distribute the bx and the c, right? FOIL. So we have 4 on the left, and then the x squared terms on the right, you'd have ax squared plus bx squared. Right? So a plus b x squared. And then the x terms, you'd have 4ax minus 4bx plus cx. So 4a minus 4b plus c. So the coefficient is 4a minus 4b plus c. All those would be the coefficients of x. And then your constant terms, you'd have 16a minus 4c. Those are your constant terms. And then I'll do the thing where we're equating coefficients. All right, so the coefficients of x squared need to be the same here. So a plus b must be equal to 0. All right, there's no x squared on the left. The coefficient of x, 4a minus 4b plus c must be equal to 0 as well, right? There's no x on the left. And then the constants, 16a minus 4c must be equal to 4, right? The constant on the left side is 4. Now I notice that all these have coefficients that are multiples of 4, so I'm going to divide everything by 4 here. That's the same thing as 4a minus c must be equal to 1. Okay. Now, I could do this where, we do some substitutions and whatnot. Like here, first equation tells me that b is the opposite of a. B would be negative a, and then I put that in the second equation. We have 4a plus another 4a, right? B is the opposite of a, so that's 8a plus c would be equal to 0. And then I see in these equations, the c's are opposite, so if I add these equations together, we get 12a on the left equals 1 on the right, so a must be positive 1/12. And then from here, b must be negative 1/12. because remember A and B have to be opposites. And then from this line, C is negative 8A, so negative 8/12, which is negative 2/3. Right. Okay. So I could have done all that, or, remember that little matrix thing I did a while back? Back to that matrix calculator thing. So if I create a new matrix, this one's called B now. There were 3 equations, so 3 rows, 3 variables, so 3 plus 1 columns, 4 columns. Down the first column, I put the coefficients of A in each equation. There was 1A, 4A, 16A. The way I originally wrote them, 16A. Then down the second column, I put the coefficients of B, 1B, negative 4B, and 0B. And then down the third column, the coefficients of C. There was no C, 1C, and then negative 4C. And finally, the numbers on the other side of the equal signs, 0, 0, and 4. All right, we get this new matrix again. This called B. You can't see the name of it. It's off the screen. I'm sorry. And then I put this into this RREF form, this reduced row echelon form. I do it for matrix B, and then change my answers to fractions over here. And you see 1/12 for A, negative 1/12 for B, and negative 2/3 for C. So exactly what I got earlier. Now, to do all that, remember you can also plug in values, right? If I plugged in 4 for X, I could find A. You'd have, 48A equals 4 divided by 48. A would be 1/12. And then just remember that A is 1/12, and then now you'd have to plug in multiple values to find B and C, but you can still do the thing where you plug in values. I just don't want to do that because I've already found, using a matrix and using these. All right, so I'm putting these in for my A, B, and C, and we're rewriting our integral. I'm going to rewrite the integral of this fraction as the integral of this, and I'm also going to split this up. I'm also going to split this up. As you see, one of these terms up here is a linear, one of them is a constant. A linear over a quadratic, we've seen some of those before. But when I had a linear over a quadratic, the derivative of the quadratic is going to be close to, if not the same thing sometimes as a linear. So this will be a nice log thing. When you have a constant over a quadratic, that doesn't work out. The derivative of a quadratic is never going to be a constant. So I'm going to split these up because these are giving me 2 different kinds of integrals to work with. Right, so we got now the integral of a over x minus 4. So a was 1/12, right? 1/12 over x minus 4 plus, and like I said, I'm going to split this up to the linear term over the quadratic plus the constant term over the quadratic. All right, the linear term, bx. So negative 1/12 x bx over this quadratic, x squared plus 4x plus 16. And then plus the constant c, which is negative 2/3 over the quadratic over x squared plus 4x plus 16. Again, the only reason I'm doing this is because these will give me 2 different kinds of integrals. I'm going to approach these in 2 different ways. Because having a linear over a quadratic is way different than having a constant over a quadratic. So I'll take these one at a time. First one's no problem. First term, I got 1/12 times the integral of, 1 over x minus 4 dx. That's not a problem. This is just what we've seen plenty of in this video. 1/12 times the natural log of the absolute value of x minus 4. Right. The second one's going to be a little trickier. So I'm going to pull the negative 1/12 out. We got negative 1/12 times the integral of the second thing is x over x squared plus 4x plus 16. I got a linear over a quadratic. And then dx, of course. So going back to like really early on in the video, one of the first few examples, a couple of them, the ones involving long division, right, where I had an improper fraction, I divided, and then we had a proper fraction, quotient plus a proper fraction. And some of those integrals, right, the proper fraction ended up like this. It was a quadratic in the denominator and a linear in the numerator. It's just that those were very nice. Those, the denominator's derivative was the numerator. That's not really happening here. All right. If I said if I had u equal x squared plus 4x plus 16, the derivative of the denominator is 2x plus 4, right, dx. All right. So that's not the numerator. All right, the numerator is just x dx, not 2x plus 4 dx. So what I'm going to do with these, and if you see a different way of doing it, fine. You might do completing the square and make a u sub, fine. But I'm going to do it this way. So I want to do some manipulation to make this numerator look like 2x plus 4. Make the numerator look like the derivative of the denominator through some manipulation. So here's how I need to do that. Well, right now I've got a coefficient of 1x. This has a coefficient of 2x. I'm going to multiply by 2 first. Now, if I multiply by 2, I can't just multiply the numerator by 2. That'll change the thing entirely. I also have to multiply by a half, which I'll pull outside. Times 2 times a half. That's just like multiplying by 1. Right? So now I have this, negative 1/24. All right, half of negative 1/12 times the integral of 2x over x squared plus 4. 4x plus 16. And then the dx, right? So one more little step is needed here. I want 2x plus 4. This is just 2x. So I'm going to just make it happen. Add 4. But I can't just add 4. That'll change the expression entirely. So not only do I add 4, but I subtract 4 as well. All right, now watch this. Okay, we're going to split this up as well. I know this is a lot, but now this integral is this, negative 1/24 times the big bracket here, because we're going to split this up. One integral is going to be really nice. That the integral of the 2x plus 4 over the quadratic, and times your dx there. But then the one with the minus 4 as well. So one of them has the 2x plus 4. That is the derivative of the denominator. And then the other one's going to have the minus 4, right? So minus 4, and I'll pull the 4 out, times the integral of 1 over, is again minus 4 over x squared plus 4x plus 16 dx, right? And then after distributing the negative 1/24 here, we'll get the following. All right, so I got, minus 1/24 times the integral of 2x plus 4 over x squared plus 4x plus 16, dx. And again, this is an easy integral to take. We've seen these early on in the video where the derivative of the denominator is the numerator. So this will just be du over u. This is just going to be the natural log of the denominator here. But then negative 1/24 times negative 4, that's positive 1/6 of this integral now. And this is the integral like the one from earlier. Remember earlier I split up the linear over quadratic and we had this constant over quadratic? Here's another one like that where you have a constant, negative 4 over a quadratic, 1 over a quadratic. So we're going to put those together in a second. All right, so yeah, so this one, no problem. This is negative 1/24 times the natural log of the absolute value of x squared plus 4x plus 16, right? Again, that's because the derivative of the denominator is the numerator now, right? 2x plus 4. Right, so keep that in mind. I did the integral there, but now we got this. Right, now we have this plus 1/6 times this integral of 1 over x squared plus 4x plus 16. And then from earlier, I'll bring this way off the page here, right? From earlier, right? Remember the third term in this integral, right? This so far has all been the second term. The third fraction is negative 2/3 times that same integral. Got minus 2/3 times that same integral, the integral of, if I pull the negative 2/3 out, this would be 1 over x squared plus 4x plus 16. And so I can put these together. It's a sixth of something minus 2/3 of that same thing, so I can combine these. Now, negative 2/3 is negative 4/6, so I have 1/6 minus 4/6, and I'm putting these both together on the final page, and we'll do this final integral. All right, and then put it all together at the end. I'm putting these together, 1/6 minus 4/6, that'd be negative 3/6, or negative 1/2 of this integral. The integral of 1 over x squared plus 4x plus 16 dx. All right, and now this integral here, let's do this. All right, so this is the final integral, and then we'll put it all together at the end. So forget the negative half for now. I'll bring that back. Okay, we're just doing this integral. Now remember, we've seen this before, integrals like this, in the previous section, in section 3.3 on trigonometric substitution. We've seen integrals like this in that video, in that section. But when I want to make a trig sub, I want a sum of squares or a difference of squares. This is not a sum of squares. It's x squared plus 16, but then you got this plus 4x. It throws things off. It's not a difference of squares. But if you recall, again, go back to the section 3.3 video on trigonometric substitution. These quadratics that are not sums of squares or difference of squares, we can make into a sum of squares or a difference of squares by completing the square. All right, so I'll do that here. So that'd be x squared plus 4x. And then since the coefficient is 1 on the x squared already, I'll leave some space so we can complete the square. I'm going to add 4, and then also don't forget, remember, subtract 4, just like I did earlier. And then we still have the plus 16 as well, right? Now this x squared plus 4x, plus 4, that's x plus 2 squared. And then negative 4 plus 16, that's, plus 12, which is the same thing as the square root of 12 squared, or, 2 root 3 squared. So now I have a sum of squares. This is x plus 2 squared plus, and then the square root of 12, again, it's just 2 root 3 square root of 12, same thing, squared. Remember, when you have a variable expression squared plus a constant squared, you're doing a trig sub. Or you might already know what the final result is, but I'm going to do a trig sub here, where you let the variable expression, this x plus 2, replace it with the constant being squared, right? So 2 root 3 square root of x times the tangent of theta, right? And then dx, right? we could solve for x, but dx would just be 2 root 3 times secant squared theta d theta. And if you got theta in terms of tangent, now you could also solve for tangent and set up a right triangle. Remember that? But I'm not going to need that here. You'll see in a second. So I'm just going to solve for tangent. You divide by 2 root 3, take the inverse tangent. So we have the inverse tangent or the arc tangent of x plus 2 divided by 2 root 3, or divided by the square root of 12. That'll be theta. All right, if I make these subs here, we have the integral of 1 dx. dx is this 2 root 3 square root of 12, right, times secant squared theta d theta. And then down here, x plus 2 is being replaced by this 2 root 3 tangent theta. So you'd have, 12 tangent squared plus, and then, 12. And if you factor a 12 out, you'd have the square root of 3 over 6 pulled out. You have 2 root 3 over 12, 2 root 3, that's square root of 3 over 6 times the integral of secant squared theta d theta over, and then tangent squared plus 1. Right, if I pull the 12 out, that's tangent squared plus 1, which is secant squared again. That makes 1. And the integral of 1 d theta would just be theta. This is the square root of 3 over 6 times theta, which if I go back to the original, is the square root of 3 over 6 times the inverse tangent or the arc tangent of x plus 2 all over the square root of 12, 2 root 3. And then, of course, plus some constant there, right? So there's our antiderivative there. And then don't forget this gets multiplied by the negative half, right? I didn't gotta do this. So times negative half, that makes this negative square root of 3 over 12. All right, so times negative 1/2. So that's a 12 down there, sorry. So negative square root of 3 over 12 times the inverse tangent x plus 2 over 2 or 3 plus the constant. Now, oh yeah, I forgot. We gotta put them all together. So I'll throw the plus constant at the end, but there will be a plus constant. All right, so after all that integral I started with, 4 over, x cubed minus 64 is, remember how I broke this up? It's going back a ways, but I started off this first term, right? The first integral, broke it up this way. This was my partial fraction decomposition. First integral was, 1/12 times the natural log of the absolute value of x minus 4. So 1/12 times the natural log of the absolute value of x minus 4. All right, that was the first one. Then we did this on the next page, which, I took this here and then broke it up to a linear over a quadratic and a constant over a quadratic. This linear over a quadratic I got was this, right? This integral. So minus 1/24th natural log of x squared plus 4x plus 16. So minus 1/24th times the natural log of the absolute value of x squared plus 4x plus 16. And then there was also this extra thing with the constant over a quadratic, which we put together with the other constant over a quadratic. And I got this, right? This minus square root of 3 over 12 times the inverse tangent x plus 2 over 2 root 3. All right, so minus square root of 3 over 12 times the inverse tangent or the arc tangent of x plus 2 over the square root of 12 or 2 root 3. And then finally, plus some constant. Here's your antiderivative of 4 over x cubed minus 64. All right, so I'm going to type all that in, and yikes, right? That took a bit, but it is doable based on things we've seen in previous sections, and also this section. So 1/12 times the natural log of the absolute value of x minus 4 minus, I'm looking for my page again, minus 1/24th times the natural log of the absolute value. You really wouldn't need absolute values around this because it's always positive for any real number, but whatever, x squared plus 4x plus 16. And then minus the square root of 3, this square root divided by 12, times the, I'll put arctangent, right, for inverse tangent, of x plus 2 in parentheses, that's in the numerator, over 2 times the square root of 3 in the denominator. And we'll lose the parentheses. And then finally, plus any constant. Taking time here, checking it out. Hooray! All right. So they rationalize denominators and stuff here, but yeah, it looks pretty similar to what I got. All right. Wonderful. And again, read through how they're doing things. Let's see, how do they do the integral? Huh, I love this. The second integral can be evaluated to find this, and the third to this, and then they put them all together. They don't show you how they did it. Okay, that's fun. Moving on. All right, so we're back to the objective with non-repeated linear factors. So let's write this out. Ah, look at this one. It's improper to start. See, the degree of the numerator is not less than the degree of the denominator. So, like way back in the early on in the video, I have to start with long division first, and then we'll look at the integral of the remainder over divisor, the proper fraction that comes from that. So I got integral of 3x squared plus 3x minus 23, right, all over x squared minus 9. So again, improper. The first thing to do when you have an improper fraction, you gotta divide these. Pardon me. So numerator divided by denominator. Lead terms, 3. Multiply 3x squared, minus 27. And I'm subtracting all of that from the line above. All right. 3x squared minus 3x squared is nothing. 3x minus no x would still be 3x. And then negative 23 minus negative 27. That'd be negative 23 plus 27. So positive 4. And there's a remainder. That's a degree smaller than this. So I'm writing it this way. The integral of rewriting this fraction as the quotient, 3, plus, and then a proper fraction where you have your remainder over divisor, 3x plus 4 over the x squared minus 9. Okay, so first one's no problem. 3x. It's the second integral that I'm going to have to do some partial fraction decomposition to, right? Because the denominator can be factored, right? When we're working with proper fractions, you factor your denominator. This is 3x plus 4 over, and then that's a difference of squares, right? X minus 3x plus 3. Right, so let's take that, do partial fraction decomposition. All right, now there's two factors down here, so I should be able to write this as the sum of two fractions, right? We're doing PFD over here. One with x minus 3 and no higher powers. One with x plus 3, no more higher powers, right? No repeats. And these are linears, so I should, powers of linears, so I just need constants a and b above those. Multiplying through by the denominator, right, you get 3x plus 4 on the left is a times x plus 3 plus b times x minus 3. I'm going to have x be positive 3 first. 9 plus 4, that's 13 on the left. And then 6a on the right. So a must be 13 sixths. And then I'm going to have x be negative 3. So that gives me negative 9 plus 4, that's negative 5 on the left. And then negative 6b on the right. So b must be positive 5 sixths. So this is 13 sixths over x minus 3. This is going to be 5 sixths over x plus 3. And I get some easy integrals with logs. All right, so putting all this together, we have 3x. I'm just going to do this here. Plus, and then this integral becomes the sum of these two integrals. So plus 13 sixths times the natural log of the absolute value of x minus 3. And then plus 5 sixths times the natural log of the absolute value of x plus 3, and then plus some constant right there. There's our final result, and type that in. Right, so we have 3x plus 13 sixths times the natural log of the absolute value of x minus 3 plus 5 sixths times the natural log of the absolute value of x plus 3, and then plus some constant c after. Great. Okay, moving on. All right, so here's another one, like there was one with the trig integrals earlier too, with the sines and cosines. But just like that one, you'll see that I can make a nice substitution here, and it'll turn it into a rational function. If I make a u sub for tangent, it will turn this into a rational integral with u instead of x. So I got the integral of 2 secant squared x over 4 tangent squared, and then plus 2 tangent. Yeah, if I do this sub here, if I replace all the tangents with u, if u were tangent, then du would be secant squared x dx, right? And that's up here, secant squared x dx, right? These become du. And this becomes 4u squared. This becomes 2u. And I'm getting the following integral. So the integral of 2 over 4u squared plus 2u, du. And you know what? This actually looks, I'm going to pause here, and this looks exactly like that integral we got in the last time we did the trig sub, or the substitution for a trig function. Okay, so I went back through in the papers I wrote earlier in the video, and look, after making the sub with the sine and cosine earlier thing, right, I got the exact same integral. All right, so I'm not going to go through all that again. But we got it. We got it earlier, and it ended up being this, right, the natural log of u minus the natural log of, 1 natural log of 2u plus 1. But here, u is tangent. All right, so this ends up being the natural log of the absolute value of tangent of x minus the natural log of the absolute value of 2 tangent x plus 1, and then plus some constant, okay? And all here u was cosine, here u was tangent, but I ended up with the same exact rational integral. So I'm just going to type this in. Sorry, I just don't want to take too much more time if we've already done the same integral before. All right. All right, so this is the natural log of the absolute value of the tangent of x minus the natural log of the absolute value of 2 tangent x plus 1, and then afterwards plus some constant. Let's see. Wonderful. All right, great. So that objective's done with the non-repeating linear factors. Right? So now we just got repeating linear factors, some with quadratics, that application one. I think those are all the objectives left. We'll see. Oh no, or it just might be the application one and the quadratic one. Yeah, those are the only two left. Good. I was like, I knew there were only 4 objectives here. Okay. So this, again, I'm just going to set up the integral for this. The volume of the solid generated by revolving the region enclosed by the graph of this function and the x-axis over the interval from 0 to 4 about the y-axis. So I've done 2 of these application problems where they're doing the volume of a solid revolution, where they're rotating around the y-axis. All that's changed here is the function and the interval. All right, so if you go back and look at those previous 2, or at least the first one, look at the first one to see how I set up the integral using the method of cylindrical shells. I'm just going to set up the integral that would result from that here. So if I did a shell for every x value from 0 to 4 and added them all up, right, we get the volume of the solid that they're talking about. All right, so I'm just going to write the integral that would result. Again, go back to that first example from this objective here if you want to refresh your memory as to how the region came about, how the solid of revolution came about, and how the integral was set up. But I'll just write down what the integral will be. So the volume of the solid that they're talking about here is going to be the integral from x equals 0 to 4, right? My interval was 0 to 4 of, the circumference of rotation, which is a revolution, 2 pi x times the height of each shell would be the value of the function. All right, so times this 6 over x squared plus 7x plus 10. And you know what? I might have actually had that same function earlier and just a 5 up here. I'm going to look back, all right, and then times the thickness, right, times dx. I'm going to look back through my papers earlier in the video. I think we had the same exact function earlier with something very similar to it. So yes, I did have a problem earlier where this was incredibly similar. This was earlier in the video. Okay, so it's not the same problem, all right, but you got 2 pi x, 2 pi x. This denominator of x squared plus 7x plus 10, the only difference is there's 6 here instead of 4. So here I'm pulling out 12 pi, right? I'll have 12 pi, right? 2 pi times 6. And when I do that, I'll have 12 pi times the integral from x equals 0 to x equals 4 of just, x over x squared plus 7x plus 10, which factors to x plus 2. It's a proper fraction, so I'm going to want to factor the denominator, try to get a PFD, partial fraction decomposition. And again, we did this earlier, right? So I'm not going to go through all this again. This x over x plus 2 times x plus 5, we got this, which is negative 2/3 over x plus 2 plus 5/3 over x plus 5. I got this already. All right, so after integrating, all right, I'm just going to jump to the end. This would be negative 2/3, so the 12 pi times negative 2/3 times the natural log of the absolute value of x plus 2, and then plus 5/3 times the natural log of the absolute value of x plus 5. All right, but this time, right, the limits are from x equals 0 to 4 this time. And that's it. Those are the only changes that were made between this problem and the problem I did previously in this objective. So once again, I'm noticing these both have 1/3 in common, so I'm going to pull the 1/3 out, make this 12 pi over 3 or 4 pi out here. And then we'll multiply by, express this, what's this, at x equals 4? -2 times the natural log of 6 plus 5 times the natural log of 9. All right, that's the value at 4. Minus, and then the value at 0 would be -2 times the natural log of 2 plus 5 times the natural log of 7. All right, all that. Okay, and then when I put all this together, you're going to distribute the negative here. The two positive ones, you'll have the natural log of 9 to the 5th. It could be 3 to the 10th power, right? 3 squared to the 5th. And then plus, natural log of 2 squared. Right, so 3 to the 10th over 2 squared times 2 squared in the numerator. And the denominator is with the minus, you have 6 squared, which is 2 squared, 3 squared. Sorry, this is tiny. 2 squared, 3 squared, 6 squared. And then minus, 7 to the 5th power. You got 7 to the 5th power down here. Now some stuff will cancel, like the 2 squareds will cancel, and then 3 squared, you'd have just 3 to the 8th in the numerator. All right. Let's just pull up. I'm just going to do this on a calculator. 3 to the 8th power is 6,561, and 7 to the 5th power, 16,807. Right? So all this together is 4 pi times the natural log of 6,561 in the numerator, and 7 to the 5th, 16,807 in the denominator, right? So this is what I'll type, and that'd be the cubic units, the volume of the shape, the solid created. And again, you can type in anything equivalent to this, and it should take it. So 4 pi times the natural log of 6,561 over 16,807. All right, so I obviously rushed things. All right, so let me try again here. All right, sorry about this. I'm going to go back and figure out my error. All right, so I see where I went wrong. When I plugged in 0 here, I put the natural log of 7, 5 log 7. I mean, 0 plus 5 is 5, right? So this should be 5 to the 5th, not 7 to the 5th, which is 3,125 in the denominator. Again, my apologies. We're like almost 3 hours in here, and I've been doing this nonstop. So my apologies for the arithmetic error again. Been a couple of these, but we get another shot so we don't lose our progress, right? They're not going to bump us back. I'll get this right this time. So 5 to the 5th is 3,125. So we got 6,561 in the numerator, 3,125 in the denominator of that log now. Okay, there we go. That's better. And 0 plus 5 is 5. I don't know why I put 7. I really don't. I'm just kind of rushing things too quickly, right? There's a lesson for you. Don't rush. All right. All right. And here we go again. This is the same kind of problem with the rotating some region around the y-axis, but the functions changed and the intervals changed, and that's all. Now, I don't think this is like one we saw before. Let me just double check my papers. Okay, so after looking through my papers from earlier in the video, it's similar, but it's not, that denominator of that function is not exactly the same as a denominator we saw earlier in the video. So I will do this whole thing. All right. So I'm just going to set up the integral that would result in finding the volume of the solid rotated by revolving this region around the y-axis through use of cylindrical shells. All right, and that integral would be this, right? So our volume here be integral would be the interval was x equals 0 to 3. The circumference of rotation 2 pi x times our function 3 over x squared plus 5x plus 6. And then times your thickness, right, dx, right? So look at this here. We got 6 pi coming out, right? The 3 times 2 pi integral from x equals 0 to 3 of just x over, and then again, we'll have a nice proper fraction. So I wanted to, factor my denominator completely. And this factors nicely to x plus 2 times x plus 3. And now let's take this proper fraction and write our partial fraction decomposition. And 2 factors down here, so I should have 2 fractions in my PFD. One of them with x plus 2, the other one with x plus 3. Once again, these are all linear, powers of linears, so I'll just need constants in the numerators, right, to keep them proper, a and b. And then multiply by the denominator if this other identity with polynomials involved. If I do that, we'll have x on the left, a times x plus 3 plus, and then b times x plus 2 on the right. I'm just going to do the thing where we plug in values. If x were -2, I could solve for a real quick. You have -2 on the left equals a on the right. And -2 plus 3 is 1. So a has to be -2. Put that there. And that's an easy integral to take, -2 over x plus 2. And then if I want to solve for b, x should be -3. So we have -3 on the left side. -3 plus 2 is -1. You have -b on the right, so b must be +3. So b must be 3. Okay, so we'll have -2 times the natural log of absolute value of x plus 2 plus 3 times the natural log of the absolute value of x plus 3. Let's write that next. So we got 6 pi, and then the integral of this will be -2 times the natural log of the absolute value of x plus 2, right, from that. And then plus 3 times the natural log of the absolute value of x plus 3. And we're evaluating this here from x equals 0 to x equals 3. And hopefully I don't make another arithmetic mistake. That's this video that I had to fix. So 6 pi times, first I plug in 3. Got -2 times the natural log of 5. 3 plus 2 is 5. Plus 3 times the natural log of 3 plus 3 is 6. There's the value at 3. Minus the value at 0. -2 times the natural log of 0 plus 2 is 2. And then plus 3 times the natural log of 0 plus 3 is 3. Now distributing the negative here, I'm going to put all these together as a single log. The ones with the positive coefficients, you have 6 cubed and then 2 squared, right? Plus, this would be plus 2. Now 6 cubed is 2 cubed, 3 cubed. With 2 squared, that makes 2 to the 5th, 3 cubed in the numerator. And then the stuff with the negative coefficients, minus, this would be natural log of 5 squared, minus 3 cubed. So you got 3 cubed, 5 squared, and 3 cubed times 5 squared in the denominator, and the 3 cubes cancel. And I'm left with 32 to the fifth and 25 in the denominator. Natural log of 32 25ths. And then times 6 pi, don't forget. There's your volume. 6 pi times the natural log of 32 25ths. Again, you could probably just type out all this up here and it would be fine. But I decided to put them together again. So 6 pi times the natural log of 32 25ths. Should be good, hopefully, if I didn't make any silly arithmetic errors. Very good. All right, so that application one, where it looked like all those problems were the same thing, rotating some fraction function region under a fractional function around the y-axis and then integrating, finding the volume with the method of cylindrical shells, right? All four of those problems I saw were like that. Hopefully those are the kinds you're seeing too. All right, so let's move on. Just the one more objective, I think, where we haven't seen too many with a quadratic that doesn't reduce, right? I think we've only seen the one where you had an irreducible quadratic. So here we actually have a quadratic that can't be factored any further, x squared plus 3 in the denominator, but it's repeated. So remember how the repeats work. It's the same as with the linears. You start off with that denominator to the first power and work your way up to the power you're seeing in the factorization of the denominator. So it's a proper fraction still. You got 7x squared degree 2 in the numerator, and then x squared plus 3 squared would be a degree 4 if you multiplied it out. So this is proper. So I should be able to do a partial fraction decomposition here. So we got integral of 7x squared over, and then we have this quadratic that can't be factored any further, squared, right? So we have a repeat, I'll write it down here, repeated quadratic, right? A repeated irreducible quadratic. So when I'm doing the partial fraction decomposition, the PFD, here's our initial fraction. The denominator is already factored completely. Now it's got two factors technically, right? There's x squared, this is x squared plus 3 times x squared plus 3 again. So I should have two fractions in my PFD. One of them with x squared plus 3 to the first power, and then with the other x squared plus 3 added on, right? You just add on to these repeats. All right, so one with x squared plus 3 to the first, the other one with x squared plus 3 squared. And these would have a common factor, a common multiple of this, right? These fractions would have an LCD of this denominator, so that's good. Now with quadratics, right? Remember I said this before in one of the previous examples. If you have a quadratic or powers of a quadratic in your denominator, putting a linear up top. So ax plus b here, right? Some linear above that to keep it proper. And then cx plus d here. So I got four constants, a, b, c, and d defined. And again, so again, powers of quadratics need linears above them. Right? Powers of linears need constants above them. Right? We've seen that plenty. Right, so now I need to find a, b, c, and d. So I multiply through by the denominator. Now on the left side, you got 7x squared. On the right side, you'd have, ax plus b times, just one of these would cancel. So you still have the x squared plus 3. Plus, and then this, both would cancel, and you just have cx plus d. And I'm going to do that thing where we equate coefficients this time. Because when there's repeated stuff and irreducible quadratics, I mean, yeah, you can do the thing where you plug in all sorts of numbers to find a, b, c, and d. It's just, I don't know, I find it takes more time for me to do that. So if I multiply these out, right, distribute the ax to the x squared plus 3, distribute the b, and then we'll combine like terms and get a identity with polynomials here, set the coefficients equal to each other. We have ax cubed. There's not going to be any other x cubes, right? So we'd have ax cubed. And then the x squareds. We'd have a bx squared and no other x squareds, right? There's ax cubed plus 3ax plus bx cubed, or sorry, bx squared, and then plus 3b, and no other x squareds. So ax cubed plus bx squared. Now the x to the first power terms, there's more than one of those, right? There'd be 3ax plus cx, right? So 3a plus c. There's a cx over here. Those would have coefficients of x. And then the constant terms, you have 3b and d. Right, so plus 3b plus d. Right, 3b here, d there. And this is all equal to, 7x squared, right? So we get our coefficients. And actually, this turns out reasonably well, right? The coefficients of a, the cubes have to be the same. So a must be 0. And the coefficients of x squared have to be the same. So b must be 7. Right? So I got a has to be 0. B has to be 7. Easy. Now 3a plus c, also has to be 0, right? The coefficients of x are 0 on both. It has to be 0 on the left side. And if a is 0, that means c must be 0 as well. Right? So this is real nice. And then the constants, 3b plus d must also be 0, right? The constant on the other side is 0. Now b is 7, so this is 21 plus d must be 0, so d has to be negative 21. Yeah, so this turns out pretty well. So if you go back up here, a has to be 0, c has to be 0. So there's no x in these linears, actually. A is 0, c is 0. So really we're just left with constants up here. That's really nice. But just know that sometimes you might end up with linears above powers of quadratics, okay? And now we're doing this. So now this integral that we started with is these integrals. The integral of 7 over x squared plus 3 dx, right? That's just 0x plus 7. And then plus the integral of, and again, c was 0, 0x plus d minus 21, negative 21 over this, x squared plus 3 squared dx. All right. Okay, so now let's work with each of these separately. Now, in both of them, I'm going to make the same trig sub. All right, so I'll actually just do both of them on the same page here, because I'm going to make the same trig sub, right? We got x squared plus 3 showing up, which is x squared plus, the square root of 3 squared showing up in each of these. So I'm going to do the following trig substitution. So this is going back to section 3.3 again. I'm going to have x be the square root of 3 times the tangent of theta. And then dx will be square root of 3 times secant squared theta d theta. Right. And then if you do the little triangle thing, that might come up. I have a feeling it's going to in this one. the tangent of theta must be x over the square root of 3, right? So then I'll set up a little right triangle. It has this acute angle theta in it, so that opposite over adjacent is x over the square root of 3, and then the other side would be the square root of x squared plus 9, x squared plus 3, sorry. And then if that's the tangent of theta, right, then theta itself would be the inverse tangent or arctangent of x over the square root of 3. Okay, so you're keeping all this stuff here in mind. Let's make these replacements in both integrals. So this integral, when I make these replacements, we've got the integral of 7 times the square root of 3 times secant squared theta d theta, right? That's the dx, over, and then, 3 tangent squared theta plus 3. Now, when I pull a 3 out, you'll have 7 root 3 over 3. I can pull all that out. Times the integral of secant squared over tangent squared plus 1, right? When I remove the 3, that's tangent squared plus 1. That's secant squared over secant squared. That's just 1. 1 d theta. So I got 7 root 3 over 3 times theta, which I'll put inverse tangent of x over the square root of 3 there. So that's no problem. Now this one, again, I'm substituting x, I'm replacing x with the square root of 3 tangent of theta. So we got plus, integral of, now this would be negative 21 root 3 times secant squared theta d theta, right, over. And then down here, I'm just going to skip to the end. This is 3 tangent squared plus 3. Pull the 3 out. 3 squared is 9. You're going to be squaring it. Then you have tangent squared plus 1 squared. Secant squared squared. That's secant to the 4th down here. And, I can pull some stuff out. Negative 21 over 9. That's, 7 over 3. 3 times 7. 3. So that's minus 7 root 3 over 3. Integral. Now, secant squared over secant to the 4th. That'd be 1 over secant squared. But 1 over secant squared is cosine squared. And now we're going back to a trig integral that we saw we saw trig integrals like this in section 3.2. So if you want to go to that video, check out those examples again, where I had powers of sine, powers of cosine. Remember, an even power of cosine, I'm going to rewrite as a half. All right, so I'll pull a half out here. We got negative 7 root 3 over 6 now, right? Because again, pull the half out times the integral of 1 plus the cosine of 2 theta. Remember, cosine squared was half of 1 plus cosine 2 theta. And now I'll integrate that. So we got negative 7 root 3 over 6. And then integrate this. This is just theta, which I can actually put together with the other theta. I got another theta from the earlier integral. And then the integral of cosine 2 theta would be, half sine 2 theta. But half of sine of 2 theta, right? I have a triangle here involving just theta, not 2 theta. Remember, sine of 2 theta is 2 sine theta cosine theta, so half of that is just sine theta cosine theta, which I can get from my triangle. All right, so I'm going to distribute this. Now, if I put this together with this, you got 7 root 3 over 3 theta minus 7 root 3 over 6. If I multiply this by 2 over 2, that's 14 root 3 over 6, minus 7 root 3 over 6. That'd be just 7 root 3 over 6 thetas, right? Because they both have thetas. All right, just putting those together. So putting these two together, I got 7 root 3 over 6 theta, and then minus, 7 root 3 over 6 times sine theta cosine theta, right? That was half the sine of 2 theta. And then we'll go back. Now both of these have 7 root 3 over 6 in common. I'll factor that out. So we got 7 root 3 over 6. And then theta, right, from earlier, theta was the inverse tangent of x over the square root of 3. and then minus, again, I pulled the 7 root 3 over 6 out, and then sine theta from my triangle. Sine is opposite over hypotenuse, right? So x over the square root of x squared plus 3 times cosine theta is adjacent over hypotenuse, so square root of 3 over the square root of x squared plus 3. All right, and then, plus some constant at the end here. Now, when I put these together, though, I'll distribute this back, actually. When we get the following, we get 7 root 3 over 6, times the inverse tangent or the arctangent of x over the square root of 3, and then minus, now you'd have 7 root 3 and another root 3 in the numerator. So 7 times the square root of 9, 7 times 3, you'd have 21x in the numerator over. And then that'll actually simplify out the 6 a bit. Right, you'd have 6 down here, and then square root of x squared plus 3 times square root of x squared plus 3 would just be the quantity, just be x squared plus 3. And 21 is, 7 times 3, 6 is 2 times 3, that's 7 halves. And if you want to distribute the 2 here, make this 2x squared plus 6, that's fine. So I'll just write this all up at the end. You got 7 root 3 over 6 times the inverse tangent or the arctangent of x over the square root of 3, then minus, and then 7x over 2x squared plus 6, and then, of course, plus some constant at the end. There's our integral. All right, so I'm going to type that out. Hopefully I didn't make any small mistakes somewhere like I have a couple times in this video. So 7 times the square root of 3 divided by 6 times the, I'll type arctangent because it takes less time. Arctangent x over the square root of 3. Oops, get out of here. And then minus, and then you have 7x over 2x squared plus 6. And then after all that, plus some constant. Right. Okay. Yeah, same setup. Right? You have a proper fraction with a denominator that's completely factored. You write up that partial fraction decomposition and then integrate, fraction by fraction, put things together at the end. Okay. All right, so I got another one that's, this is incredibly similar to what we just did. But here's the thing though, the integral we just did, previous example was 7x squared over x squared plus 3 squared. So yeah, not a lot is going to change. But it'll change enough to where I do want to write it out. So that is unfortunate, but I'll write it out again. So let's get this on paper here. Integral 7x squared over, and then once again we have one of these quadratics that's not factorable. That's a repeated factor. All right, x squared plus 2 squared. All right, so once again, like the last example, again, very, very, very similar to the last example. When I'm writing the part, the denominator, it's a proper fraction. The denominator is already completely factored. There are 2 factors down here. There's x squared plus 2 and x squared plus 2 again. So I should have 2 fractions in my PFD. One with x squared plus 2 to the first power, and then another with x squared plus 2 to the second, right? You just keep going from the first power up to the power that you see in the factorization of the denominator. You keep going up to that power in the PFD here. And since these are all, once again, these are all powers of quadratics. These are all powers of quadratics. I'm going to say the numerator could be up to a linear. Right? So ax plus b for the first, and then another power of a quadratic here, so a linear polynomial above this, cx plus d, just like last time. I multiply through by the denominator, so we got 7x squared again over here. This first fraction, I have ax plus b times just, one of the factors of x squared plus 2, plus, and then here would just be cx plus d again, right? Because again, both of those would cancel. And if I gather the like terms, distribute the ax, distribute the b, you'd have ax cubed again, and plus bx squared, and plus 2ax plus c, right? So 2a plus c times x, and the constant term would be 2b plus d. Right, so all that change from last time was instead of, 3, you have 2 here, 2a plus c, and instead of 3, you got 2 here. Right? And this needs to be 7x squared, right? So clearly a is 0, right, because there's no x cubed. B must be 7 again. And if a is 0, c must be 0, right, because the coefficient of x has to be 0. And if b is 7, now this would be 14 plus d must be 0. So d must be negative 14. All right, so I got the constants. I'll just pop them up here. So a is 0, c is 0 again. Now again, this doesn't always happen. Please understand this. All right, just because this happened in the last two examples doesn't mean it will always happen. You may end up with linears instead of just constants above these quadratics or powers of quadratics. And then b is 7, and d is negative 14. Right. So we're taking the following integrals. So now I'm doing integral of 7 over x squared plus 2, and then minus, the integral of 14, or plus the integral of negative 14, but I'll just do minus 14, and minus 14 over, and then x squared plus 2 squared. And very, very similar. So see how both of these have a sum of squares, right? X squared plus, and then the square root of 2 squared. So I'm going to have x be the square root of 2 times the tangent of theta, right? Do a trig sub. Dx then would be the square root of 2 times secant squared theta d theta. Then your triangle here, right? The tangent of theta would be x over the square root of 2. And then this side would be x squared of x squared plus 2. And then theta then must be the inverse tangent, or the arctangent of x divided by the square root of 2. Okay. So doing these things to both these integrals. Now this here, all right, so if you look at the last example, okay, I'm just going to kind of skip to the end. You'd have 7 root 2 secant squared theta d theta. And down here you'd have 2 tangent squared plus 1, but you pull the tangent out, you got 7 root 2 over 2. Pull the 2 out, and then you have tangent squared plus 1, which would be secant squared, which would cancel the other secant squared. You would just have the integral of 1, so just theta. Right, this would be 7 root 2 over 2 times theta, which we'll replace with the inverse tangent of x over the square root of 2 in a second. Then minus, and then something very similar here. 14, and then dx is root 2 secant squared. So 14 root 2 secant squared in the numerator. You'd have 2 tangent squared plus 2. Pull the 2 out, square it. You got 14 over 4. 14 root 2, that'd be 7 root 2 over 2. I guess it'd be 14 root 2 over 4. So 7 root 2 over 2. And then times the integral. And you have secant squared up top, and then tangent squared plus 1, but squared, secant to the fourth on the bottom. So just like the last example, you have secant squared over secant to the fourth. That'd be 1 over secant squared or cosine squared. which again is half. So I pull the half out. Half of 1 plus cosine 2 theta, right? Cosine squared is half of 1 plus cosine 2 theta. And then we have minus 7 root 2 over 4, right, times, and then the integral of this stuff is theta plus, and then remember this was half the sine of 2 theta, which if I do half the sine of 2 theta in terms of just theta, that's sine theta cosine theta. And again, you saw all this in the last example. Now distributing this, and then I can put this with the theta together with that with the theta. All right, so this would be, 14 root 2 over 4 minus 7 root 2 over 4. That's 7 root 2, positive 7 root 2 over 4 times theta, and then minus, 7 root 2 over 4 times sine theta cosine theta, and then we'll put everything in terms of x. All right, again, I know I rushed this one, but this is very, very similar to the previous example. Now theta, right? Theta is the inverse tangent of x over the square root of 2. So we have 7 root 2 over 4 times the inverse tangent or arctangent of x over the square root of 2 minus, and then 7 root 2 over 4. Now the sine of theta be x over the square root of x, opposite over hypotenuse, right? X over the square root of x squared plus 2. And the cosine of theta would be square root of 2 over the square root of x squared plus 2. And then you got, square root of 2 times square root of 2 would be 2. Goes into the 4 twice, right? So those are all gone. And these make x squared plus 2 down here, and I'll distribute the 2 to get 2x squared plus 4. So we got 7 square root of 2 over 4 times the inverse tangent of x over the square root of 2, then minus, 7 times x in the numerator there, and 2x squared plus 4 in the denominator, right? And then, of course, plus some constant at the end. So that's what I'm typing in. I'm really hoping this is the last problem. Looks like my progress is close enough. So we have 7 times the square root of 2 divided by 4, and then that times the arctangent or inverse tangent of x divided by the square root of 2. And minus 7x over 2x squared plus 4, and then plus some constant. That should be good. Great. And it looks like I finished it. Looks like we got 100%. Hooray. The assignment is complete. All right, so as I was saying at the top of the video, just be aware that the questions I saw here may not be exactly the same questions you see when you work on the assignment yourself. But, the objectives are all the same. So I'm hoping, the problems and the way I did them will be similar enough to the way you're going to do them and help you out when you work on the assignment yourself. Great. And thank you very much for watching.